technical sales. So $50 off each of those courses. We also have a package of safety courses. We have been lucky to get 3 rounds of OSHA grants to do solar specific safety training. 2 of these classes are available packaged together for $99. That was originally $278 if you took the 2 of them separately. We also have our 3rd round OSHA class, which is currently running on battery safety. That is available for free if you are in the United States and working in the solar industry or hoping to get into the industry. And you can find that on our website, solarenergy.org. We also have some on-demand classes that you can take at any time. You don't have to wait for a new session to start. And these cover different short topics like code updates, some basics of site analysis, tools and techniques for the solar industry, a couple different options there. So before we get started, let me tell you a little bit about myself. I work for Solar Energy International full time. I'm a curriculum developer, and I also do some training on the side when I'm not updating courses. I also moonlight for SEI Professional Services, which is our sister company. It's an engineering firm that does things like design plan sets. We do site reviews, inspections, commissioning, troubleshooting, performance verification, all kinds of technical things. We do not do construction itself, more things surrounding the engineering side of the industry. You can check out their website also. I am a NABCEP certified PV installation professional since 2006, and I have been in the industry for over 15 years now. I started out working for a solar installer, was with that company for a little over 11 years, did everything from installation to sales, got into project management, and ended up the director of construction for the East Coast. And then about 4 years ago, I left that company to work for SEI full time. In this class, we're going to cover a lot of the common mistakes we see when we are inspecting PV systems. Some of the things we look for are equipment that's not being used properly. It is listed for one use and it's being used in some other way. Wiring is a huge issue that we see when inspecting systems, and we're going to look at a couple different reasons that wiring can become an issue. Things like wire being used improperly, poor connections, not supporting it properly. We'll look at that in detail. Labels, it's a pretty big deal. There's a large list of labels required by several different codes, including the National Electrical Code. We need to make sure that we have the proper labels where they should be located, and we want to make sure that we don't kind of go overboard in the labels as well, because that's just additional expense that is unneeded. Grounding is a big problem, or it can be a big problem. I should say lack of grounding or poor grounding. We'll take a look at that. Array wire management is one of my pet peeves. It's something that is easy to do poorly and not that much harder to do really well. So we'll take a look at that. We're also going to look at how we mount the system, our penetrations if we're doing a roof mounted system and how those are flashed. We'll also look at some issues with ballast mounted systems. And finally, we'll look at some issues with expansion fittings or lack thereof. National Electrical Code 110.3b and C and 690.4b state that the equipment that we're using must be tested and listed for the application that we are using it in. It has to be tested by a nationally recognized testing laboratory, or a NERDL. We need to also make sure that that equipment is being installed according to the instructions. We have a saying at SEI, read your free manual, RTFM, that is really important because those instructions are going to give you the requirements that come along with listing that product. We've got an example here. This is an indoor rated lug. It is an aluminum lug, not designed for exterior use. That's only been installed for a couple of weeks, and we can already see that we've got some white spotting on that aluminum where it's starting to corrode. That should be a solid copper lay-in lug that is tinned, and that would be the proper equipment for this situation. So we need to make sure that what we're using is rated for our environment, it's rated for voltage and current, and that we're using it according to the manufacturer's instructions. 110.3b says the equipment must be listed and rated for the location that it's being used in. NEMA ratings are the weather resistant rating of the equipment. They come in different levels. We typically see things like inverters rated to NEMA 3R, which means they can be installed outside in certain locations, in certain orientations. There are higher ratings. The NEMA 4 ratings are more water and weather resistant. Table 310.104a gives you all the conductor properties for different conductors. We can see in the picture here, we have some THWN2, which is not sunlight resistant, being used outdoors, and that exterior coating is already falling off. We don't know exactly how long that's been out there, but probably not that long because that wire is not rated for that application. We also need to make sure that the equipment is rated for the type of voltage we have, either AC or DC, the voltage rating. So we're working with a 600 volt system, 1000 volt, 1500 volt. We need to make sure that all of our wiring and equipment meets that voltage rating. Obviously, it has to be rated for the current that we are using in the system, that we're going to have in the system, and it has to have the proper AIC rating. Again, we can't stress this enough that you have to follow the manufacturer's instructions. You can't take something that is rated for indoor use only and put it outside. You can't use a 600 volt wire in a 1500 volt system. You know, these things would seem pretty obvious, but these are mistakes that we often see in the field. Electrical connections are really important. If the connection is not made well, it can lead to increased resistance. And anytime we have increased resistance, we have increased heat, and heat can lead to fires. So we need to use the proper wire for the application. If we are using fine stranded wire, for example, this battery wire we can see at the top left, we need to make sure that any terminal or connector that is going to attach to that wire is rated for fine stranded wire. We see this most with battery based systems. We also don't want to mix dissimilar metals. They will have a galvanic reaction and will corrode over time. Specifically, in our systems, we don't want to mix copper and aluminum unless the terminal that it's going into is specifically rated for working with both copper and aluminum. A lot of times we'll see copper that's tin plated, like the lug we see at the top right photo, and that will protect the copper that's on the inside of that lug from any kind of galvanic reaction. Double lugging, a terminal is only rated for one conductor unless it is specifically identified as being rated for more than one conductor. So you can't put two or more conductors in a lug unless it is specifically listed for that purpose. And there are very few lugs out there that are rated for having more than one conductor. When we are making our connections, we need to use the proper crimp tool and the proper terminal for that connection. This is especially important for our PV module interconnects, like the MC4 connectors we see on the bottom right. This has become a huge issue in the industry of using connectors that are not intermatable, is a new code-defined term, two connectors that are listed to be used together. And as of now in the industry, there are no connectors from different manufacturers that are listed to work together. So if you have an MC4 connector, you must use all MC4 connectors. If you have an Amphenol connector, you must use all Amphenol connectors. Same for any other type of connector. Always use the same type of connectors because connectors are one of the leading points of failures in PV systems. And here are some examples of those failures. We can see the top left photo, the connector was not made properly, and that little screw-in piece that seals where the wire goes into the connector has fallen off. We've got a couple of connectors that had high resistance connections, which led to a fire and melted those connectors. The bottom right-hand side, we can see a connector that's broken apart when we've exposed the connection inside the plastic casing there. And finally, in the bottom left, we have an equipment grounding lug that has a couple issues here. First off, we've got THWN2 green wire, which is not sunlight rated, used outdoors underneath the array. That is technically a code violation. It's not rated for that environment. We also have two wires double lugged in here. You can see one wire coming in from that direction and this other wire coming around, and they're both under there. So that's double lugged. That is not rated for double lugging, so that's a code violation. You also have all these strands that didn't make it underneath the terminal. So that is poor workpersonship seen right there. National Electrical Code requires that all terminals be torqued to the manufacturer's settings. In almost every case, if there is some kind of set screw terminal, there is going to be a torque setting specified by the manufacturer. They'll give you the torque requirement for that terminal. It is almost always provided. I think I've only seen one case where the torque setting was not provided by the manufacturer. We have to calibrate that terminal to the required torque setting if the setting is given. Now, if they provide alternate instructions, we can follow that. The only case that I could think of is a terminal that is a clamp down terminal. A lot of inverter manufacturers have terminals where you have to put a tool in to open the terminal up. You put the conductor in and pull the tool out and it clamps down on it. Obviously, you don't have to torque those. They're self-torquing. We also need to read the instructions of our torque tool. We need to know how to set that tool properly, and we also need to know how often it needs to be calibrated. We are using these tools often. They're going to be out of calibration eventually, so we need to send those in to be properly calibrated. So here's what happens if you do not properly torque your terminals. On the left-hand side, we can see a fused disconnect where that has melted. It's really hard to tell here if it was the terminal or the fuse that failed first, but we can see that that has melted one way or the other. So that disconnect is going to need to be replaced. On the right-hand side, we can see what is commonly referred to as a Polaris connector. Here's the good connector in the bottom right there, and there was a high resistance terminal in this connection here. So this little metal block is what's inside of this plastic coating. So it originally looked like this, heated up, melted the plastic casing right off of it. Looks like it had a ground fault to the side of the disconnect as well, burned up all these wires here. Now, this looks green, but that's just corroded copper on the inside of this. This originally was a black wire. Obviously, there was a high resistance connection there, a loose terminal, and that caused heat and eventually melted that connection. Labeling is really important. We have several different requirements in the National Electrical Code for labeling our equipment. We have to follow those requirements. There's also two informational notes in the NEC that refer to ANSI standards for the coloring of both the label and the text on the label. So it's important to find those. And 690 will give us the specific size and color that we need to use in our labels. Now, I want to point out that this system on the picture here is over labeled. There's too many labels here. Some of them are not in the right place. And that's just adding to confusion, unnecessary expense. So we need to make sure that the labels are in the proper location, that we have the right label on the right piece of equipment. Now here's a table of where specific labels go. I'm not going to go into this in detail. You can refer back to the slides later and take a look at this. I will also say that Hellerman Titan has really good posters for each code cycle that clearly shows what labels are required where. And the labeling is going to vary again depending on what code cycle you're on. One thing I do want to point out is label number 1, this warning photovoltaic power source label. That's supposed to be installed on conduit and any boxes that contain DC circuits. That is not required on the AC side of the system, and try not to let your AHJ or inspector bully you into putting that on the AC side of the system, because that is not a code requirement. And again, that's just adding extra expense to the system. Workspace is really important. We have a couple requirements for workspace, and the NEC tables 110.26A1 and 110.26 has the text for systems that are under 1,000 volts. The table will give you different requirements based on the voltage of the system and the condition in which that system is installed. And 110.30 and table 110.34a give you the requirements for over 1,000 volts. This is going to give you enough space to work around the equipment. We don't want to be working in a situation where we're jammed right into that equipment, which is going to increase the chances of electrical shock hazard and arc flash hazards. So we want to make sure that we're following those proper working space requirements. Now here Here's a really interesting photograph here. You can see that they've set up their work table here, and they've got all kinds of junk in front of this electrical equipment. Code requires a minimum of 3-foot space in front of this equipment, so this does not meet the space requirements. We also have this box in the corner here. We don't know what's inside that box until you open it up and find out there's another piece of equipment in there. So that's electrical equipment surrounded by a box. Definitely does not meet the working space requirements there. I don't know what they were thinking when they put that thing inside the box there. I don't know if it was to protect it from the door that we saw swung open in the previous picture, but that is definitely a code violation. The National Electrical Code is not the only thing that we need to follow when it comes to working space. We have to follow the manufacturer's requirements also. So we need to RTFM, read our free manual, look and see what the requirements are for space between our equipment and other equipment, our equipment in walls, doors, things like that. Here's an example of an SMA inverter in the picture on the right that is butted right up against another piece of equipment that looks like some kind of combiner box. And on the left-hand side, we have the working space requirements from the manufacturer's manual. We can see that we need at least 11.8 inches or 300 millimeters between equipment. So that is a working space violation there. We can also see all this wire hanging out the bottom of this box, no conduit there. That would be a violation as well. Now, color coding can be a little confusing, and the confusing part is it varies depending on what code cycle you're on. One thing that does not vary is the color of the equipment grounding conductor, which must be green, green with a yellow stripe, or bare copper. That's our equipment grounding conductor. Any solidly grounded conductor, which is a conductor that has a solid connection to ground, must be white or gray. A good example of that is our neutral conductor on the AC side. You will see in older code cycles white or gray used for one of the DC conductors, but in code cycles after 2017, that is no longer considered a solidly grounded conductor. It is now a functionally grounded conductor or an ungrounded conductor. And those are allowed to be basically anything except green, green with yellow stripe, bare copper, white, or gray. It can be black, red, blue, orange, purple, any of those different colors. There is no code standard for that. There are some conventions that we use for color coding. Typically on the AC side, we use red and black for lines 1 and line 2, and there are other kind of standard conventions for three-phase systems as well, depending on what type of three-phase system it is. These are not code requirements, but they are industry best practices. On the DC side, there's kind of two different schools of thought in the way to do it. Some installers are using red for the negative and black for the positive. That seems very common. Another way to do it is to standardize on colors that you would not typically use on the AC side, like purple and orange for the DC side. That way you can easily tell when you're working on a split phase system which conductor is DC and which conductor is AC. So you'd use red and black on the AC side and then purple and orange on the DC side. Now let's take a close look at this picture on the right. We can see that we have two DC PV source circuits coming into this inverter. We have red being used for the positive and black being used for the negative. That's all good. We have our green equipment grounding conductor, which is bonded to the conduit and then goes into this bus bar down at the bottom. That is good as well. But they marked their two different strings using white tape and green tape. Now, I'm just kind of face palming here. I don't know why they did that. Those are literally the only two colors that you're not supposed to use on ungrounded conductors. And that's what they used. They could have used blue tape, orange tape, any kind of other color tape except white and green. White being the marking of a solidly grounded conductor and green being the marking of an equipment grounding conductor. So code violation there. That was just such a simple thing that they could have easily done differently, and they didn't. We just want to make sure that those are not going to get confused by someone coming to troubleshoot the system later. Equipment grounding conductors are really important. They are our connection between all of our non-current carrying metal parts and the ground. They provide a path to ground, a easy low resistance path to ground for any fault current. It's what allows our overcurrent protection devices and our ground fault detection system to work properly. And having improper grounding connections is a common failure point for inspections. On these two pictures, we've got a couple different things going wrong here. First off, they're using a green THWN2 wire, which is not rated for sunlight. So that is a code violation. That should either be bare copper or USC2 or PV wire. We also have an automotive type connector there. This is not the proper use for that type of connector, so that's a code violation. And you've got the connector underneath that mounting block, which is not the way it's designed to be installed. So that is a violation of the installation instructions of that S5 mounting clamp. So lots of different violations there. It's best to use a rack that is rated for UL 2703. That is a self-bonding racking system that makes it a lot easier. This S5 PV Direct kit is UL 2703 listed, so that will automatically make the connection between the clamp and the module. And we do need to RTFM and install that racking and the grounding properly. We should use a lay-in lug that is rated for this environment on the module. That would be the proper way to do it. We also need to make sure that we are managing our wire properly. We're going to look at that a lot more closely in a couple slides. And we need to prevent ground faults between our module frame and the racking. Specifically, we want to make sure that there's no PV source circuits pinched underneath that module and the racking, and we want to make sure that that is put in conduit. Let's look at some array wire management. We've already talked about using equipment that is suitable for the application. In this case, inside the array, we want to use USC2 or PV wire. That is single conductor cable, which is allowed to be within the array as long as it is not readily accessible. It needs to be rated for the proper voltage and has to have the proper connectors using the proper crimp tool. We saw the results of what happens if you don't have the proper connection a couple of slides ago. Now, what is readily accessible? We're going to look at the actual definition in a minute, but underneath the array, especially in a roof mounted system, is usually considered not readily accessible by most inspectors, but really it is going to be up to your AHJ as to whether they consider that readily accessible or not. So good to know what inspector you're working with and what their expectation is going to be. This wire also needs to be physically protected from damage. This can be from environmental conditions like ice, wind, rodents. We get a lot of squirrels here in the Northeast United States that like to get under the array. Also, the wire can't rub against stuff and it must be able to move when the system heats up and cools down for that thermal expansion. We're going to look at that a little bit more in the future. Now, these pictures at the top here, we can see this is a combiner box. We have several PV source circuits coming in and being combined. This box was built in a prior code cycle where one of the DC PV source circuits has white coloring. It was considered grounded. And we would not see this in a system installed in the current code cycle. I also want to mention that this is in the process of being installed and our PV output conductors have not been landed yet. You'd have the negative coming out of this block here and the positive coming out of this block right here that hasn't actually been installed yet. It would go out of this conduit right here. So we only have the PV source circuits coming in. Now, there's nothing wrong with this. This would have been acceptable under the code cycle it was installed in. If you look really closely here, we can also see that this terminal has been torqued. We can see that red line there of the torque mark on that nut there. That's really nice. The wire management in this is excellent. It's all nicely bundled together, all very clearly labeled, and we'll see some more examples of that closer up in another slide here. The bottom picture, we've got our PV source circuits in this nice wiring harness here. Everything is nice and clean, all well bundled up. That is an excellent job there. Neat work person like manner that they did a good job on that one. We want to make sure that we are doing a really good job managing our wires underneath the array. When I go out to inspect a site, the first thing I do is look underneath the array to see if there's any wires hanging down. I think that is an excellent indication of the quality of the installation. If the installer took the time to really concentrate on good wire management, there's a pretty good chance that the rest of the array will also be of high quality. If I go and show up and there's wires dangling everywhere, I am definitely going to take a very close look at all the parts of the installation to make sure that it is all done properly. Code requires that our PV wire and our USE2 be secured within 300 millimeters or 12 inches of any box, and then every 4.5 feet or 1.4 meters. And single conductor cable can only be used within the PV array. It cannot go outside of the PV array. And it must be not in a readily accessible area, or if it is, it must be in some kind of conduit or raceway. As I said when we started this, bad wire management is really easy. It's easy to slap wires down and not really care about it. But really, good wire management isn't really that hard. And this slide used to say that good wire management is difficult, but I don't think that's really true. We have lots of different techniques that we can use to install wires easily. It just takes some pre-planning and a little bit of thought and the proper equipment to do it right. We need to keep in mind that if our wires are all hanging down and sloppy on day one after the installation, on day 9,000, which is a little over 24 years later of the system that is typically designed for a 25-year lifespan, what's that going to look like? If the wires are hanging down and rubbing against an asphalt shingle roof over time, it's not going to take long for that sandpaper-like asphalt to wear away the insulation on that conductor. So we have all kinds of different ways that we can manage our wires. We have racking systems that have integrated wire management wireways, snap and rack, and other U-type channeling is very easy to manage your wires. There's also ballast mounted systems that have wire management trays built right into the racking itself. When we're behind our modules, there are all kinds of clips and cable ties, stainless steel coated one, there's hooks. And one technique that I like to use, especially on roof mounted systems that are using a rail based racking, is to use the grounding conductor. That equipment grounding conductor is going to be going across the rails. It's securely attached to the rails with the lay-in lug that is bonding the rails together. And you can use that to carry your PV source circuit conductors. You can bundle them together on that equipment grounding conductor, which is typically a larger gauge conductor. It's a little more stiff. That is a technique that works really well. Anytime we're going into an electrical box, we need to make sure that that entry is sealed properly. We need to have conduit going out of that box. And the reality of the situation is that all of these boxes are going to get some kind of water in it. Code allows us to have a weep hole added into all electrical equipment for drainage. I've seen pictures of combiner boxes like we saw in that last slide, where they were mounted underneath an array and water had gotten into that combiner box, and 3/4 of that combiner box was a solid block of ice because it had frozen and had no accommodation for that water to drain out of the box. So in that case, a small weep hole would have saved that combiner box, and that's thousands of dollars to replace that box. They're expensive to begin with, and the labor it takes to install that is pretty significant. Here we see a couple examples. This is a really nice wire management done here on these poles. That wire is all nice and secure. We can see again, this is an older code cycle with the white wire there. We wouldn't see that in a system that's under the current code cycle. In this one, these guys are on the roof there, laying down underneath those modules, doing their wire management. It's really important to plan ahead and think about this racking system that I'm using, what accommodations does it have for me to do the wiring? A lot of ballast mounted systems will allow you to tip the modules up so you can very easily go along and wire underneath them and then lay them back down. That's just going to make it so much easier for the installers if the designers do a little bit of forethought ahead of time and think about how they're going to do that wire management. Make sure that they have the equipment, the cable ties, clips, hooks that they need to manage that properly. 690.31a says any DC PV circuit over 30 volts that is installed in a readily accessible location must be guarded or in a raceway. So what is readily accessible? That is any place that you can get to the wiring without using a tool or having to climb over something or having to use a ladder. If I can walk up to that array and just touch the wiring, that's readily accessible. In a roof mounted system, this typically isn't an issue because we're up off the ground. You'd need a ladder to get up there. But for our ground and pole mounted systems, it becomes a problem that is definitely readily accessible. So the ways that we can meet this requirement are fencing the system, like we see in the bottom left-hand corner, which is very common for large scale ground mounted systems. Or we can put some kind of barrier behind the array. We can see in the right-hand photo that they used metal lath there behind the racking to protect that wiring. That is acceptable. One thing I'll note about this metal lath is we often call it a blood lath because when you cut that lath, all these little edges that you can see at the top here sticking out are like little razors. They're super sharp. I actually cut the back of my wrist on one of these one time and had to go to the hospital and get a bunch of stitches. So be careful with that. There are lots of other options as well. I've seen people use composite lattice work. I've seen rubber coated chicken wire, stainless steel chicken wire. I've seen fabric. There's lots of different options as long as it's physically protected and it is acceptable to your AHJ. That's the important thing. Something that we see with pole mounts often is raising the height of the array to above 2.6 meters or 8.5 feet. That is considered inaccessible. You would need a ladder to be able to get to the wiring. So as long as that wiring is above 8.5 feet. Now, it doesn't necessarily mean the bottom edge of the array. Say this edge here, there's no wiring in here. So you would just need to be 8.5 feet from this point where that second rail is. That would meet the requirements as long as it's acceptable to your inspector. 690.31b has a bunch of requirements for identification of our PV source and output circuits. They must be marked and identified at all point of termination, connection, or splices. So it has to have the circuit number there, and code now requires that they be identified as positive or negative. There's a couple different ways you can do that. And if you have conductors from multiple PV systems sharing the same junction box, raceway, conduit, they need to be grouped separately so that you can easily identify which goes to which. And I'll give you a really good example of why. I was doing a 50 kilowatt PV system on a commercial building that had 3 separate arrays. Each array had their own separate inverter, but the inverters were in a central location. So the 3 inverters were all together. The wiring from the 3 different arrays came together in a junction box and into a conduit at a location that was separate from the inverters. So you had 3 different sets of PV source circuits all coming into a conduit and going down into the inverters. The electricians that were installing the wiring did not do a good job of identifying which wiring was which, and they had the positive from some of the strings going to inverter 1 and the negative to going into inverter 2, and they had mixed them all up. So that was not properly installed. Luckily, we found it at commissioning, so that wasn't an issue, but they had to go back and rewire part of that system. So that's why we need to group those wires together in any kind of junction box or wiring trough. In these pictures, we can see this is the marking from that previous combiner box. It tells you it's combiner box 2 and what string number it has. These are high quality labels. They're not going to come off. They're not going to fade over time. That is an excellent marking job. Code also requires that DC conductors be separate from AC conductors in wiring enclosures, cable, or raceways. The exception here is these wiring gutters down here. This is not included in that requirement. So you actually could mix AC and DC in there as long as it's acceptable to your authority having jurisdiction. You cannot put any non-PV circuits in the same conduit or raceway as a PV system circuit. So those would have to be separate. In this picture, we have separated the DC and the AC circuits. So that would be acceptable. Sometimes the inspector will require you to separate them in a trough like this. It's all going to be up to that AHJ. Any DC PV circuits being run inside of a building must be contained in a metal raceway, metal enclosure, or metal conduit. And that's from the point of penetration into the building to the first readily accessible disconnect. Here in the center picture, you can see a residential system. You've got a couple of different arrays on this roof. They're using EMT, which is electrical metal tubing, which is an acceptable use there. You could also use type MC cable, which is a metal clad cable like we see in the bottom left-hand photo. The photo on the right is a commercial building also using EMT conduit. This does not apply to microinverters, which has an AC output circuit. You would not need metal conduit for microinverters. You would need metal conduit for DC optimizers, which are still a DC circuit. So any DC circuit in the building needs metal conduit. If it is on the outside of the building, it does not need to be a metal conduit. This is only on the inside of the building up to the point of the first readily accessible disconnect. Let's look at some pictures here. This photo we've seen already. This is the larger version of it, of an excellent job of wire management. We can see they have flipped this top module so the junction box is facing down, and then the bottom row of modules, the junction box is facing up. So the 2 junction boxes are directly opposed to each other. And then the wiring just has to make a little short jump into this wiring trough here, and that makes wire management very easy. One thing I will mention with these upside down junction boxes, it is very important to read your free manual from the module manufacturer and make sure that it is an acceptable way of mounting that module. Some modules cannot be mounted upside down. The problem is there's a weep hole in the bottom of the junction box, and when you mount the junction box upside down, the weep hole is now at the top, and when moisture travels down the back sheet of the module, it goes right into the junction box. So read the manual, make sure this is acceptable. If it's not acceptable, then you have to mount it the other way with the junction box at the top, which is going to make wire management a little more challenging. Again, pre-planning and reading the manuals and thinking ahead of time is really important in a situation like that. Here's another good wire management. Here we have an older code cycle system. We have a large commercial combiner box with a whole bunch of different circuits coming into there. It looks like about 24 different circuits. The wire management is all excellent. The only issue we have is the top of this piece of short conduit here. It's good they used conduit because that's not technically underneath the array, but water can just go right into this conduit and down over the fuse into this combiner box. This needs to be sealed at the top. It would have been better if they used some type of weatherhead that was sealed. That would have prevented water from getting into that box. So that's a little bit of an issue there. Now let's look at the ugly side of wire management. Here we can see this is not underneath the array. We've got some PV source circuits just hanging in free air there. That is not acceptable to code. We're using non-insulated wire staples there. That's not a good idea also. Here, this is just kind of a jumble mess of wire in both these situations. This doesn't look to be sealed properly either going into that conduit. We have green wire there. It's always a red flag for me because very rarely is that USC2 or PV wire. It's usually just THWN2. We've also got some zip ties there. I'm not a huge fan of zip ties. I don't think they'll last the life of the system. These zip ties will pop and this wire will just be hanging down in no time. DC conductors inside of a building must be run in metallic conduit. This is not run in any conduit, stapled right to the rafters. Uninsulated staples there. This is just a nightmare waiting to happen. I mean, this is DC conductors here, just hanging out in the attic. Here, they're just run straight across the roof. This is not underneath the array. That should be in conduit. It is definitely a code violation. I think that's exposed to the sun, which it is sunlight rated, but still the sunlight's pretty harsh on those conductors. And it's laying directly on the asphalt shingles. That's going to rub the insulation away in no time. And there's going to be ground faults all over the place. You're also going to get parallel arc faults in here because I can almost guarantee those conductors are going to wear off and you're going to start arcing between those two conductors. So that's a really bad situation. Here's some more examples of conductors not used properly. Here we've got a bunch of different UF conductors going into this conduit and a jumbled mess there. Down here, we've got conductors going right across this sharp edge of the racking there. I have seen situations like that cause ground faults before, so that's not going to last very long. This one almost looks like it's about to be pinched between the racking there. Down in the bottom right, we have conductors going into this junction box. There's no strain relief clamps here to seal this and protect the wire from pulling out of the junction box. It almost looks like they started drilling the hole for the strain relief clamp, probably realized that they ran out and said, nah, forget it, we'll just drill a hole. And they didn't even caulk it. So that's obviously a code violation. White zip tie, that is not rated for the environment. That's going to fall down. We've got green THWN2. That's not rated for the environment either. This junction box is just drilled right to this metal roof. There's probably better ways that they could have done that. And the lid of the box is open. So that's not even closed. So that's not good. You're going to get all kinds of water inside that box. Top right, we have PV conductors just run right across the roof there. That is not acceptable. That should be underneath the array or in conduit. Same thing with this equipment grounding conductor here. At least it's bare copper wire. They didn't use green wire on that. So that's a plus, but still needs to be managed properly. Just more wiring errors. These ones on the left-hand side, both this picture at the center bottom there and this one on the left, this is a wire bending radius violation. Those wires are bent too tight and this one especially, and they're pulled really tight, so there's not a lot of space for expansion and contraction. Um, this one, obviously, this MC4 connector is not made up properly. Also, same thing, no strain relief clamp going into this box, just a hole. And this box is actually just glued to the roof, so that's not going to last very long. Here, I mean, it's pretty obvious what's wrong here. If I see this when I show up to a job site, I'm going to take a close look. This array really needs to be removed, and this wiring needs to be reinstalled. Green THWN2 wire, again, also that is not acceptable as far as code goes. This one in the top middle is an interesting situation. This is a system that I was inspecting. We were doing mega ohm testing, insulation resistance testing on these PV source circuits to ensure that the insulation was intact. And all of them were measuring fine. I think they were in high multi-giga ohm, except this one string. It was an interesting situation because the resistance reading that we got on that string was a passing reading, but it was significantly lower than the rest of the strings. And we were all kind of scratching our heads saying, okay, well, that's a passing number, but it's still very different than the rest of the strings. So we had some extra time, so I tracked down the circuit and found this MC4 connector laying literally in a puddle on the roof. So obviously the wire management on that job was not good. The water soaked MC4 connector was causing some leaking of current to ground. As soon as we pulled that connector out of the puddle, we let it dry off for a little bit, secured it to the racking, and retested that string, and it tested high like the rest of the array did. So that was the issue there. Other just really bad wire management. Here we've got a sharp piece of conduit, flexible metal conduit here. That's going to, we see it already has worn away some of this insulation here. Same thing down here with this conduit. Up here, I mean, talk about wire bending radius. This one's bent almost in half. Same thing down here. These are coming out of this piece of conduit here so tight that this is just going to cause a ground fault over time. This is what the wire management looked like when we showed up on the array. Wire just hanging all over the place, drooping across the ground. There was literally no wire management there at all. And this is what it looked like when we're done. Everything is nicely secured, no wires hanging down, plenty of loops. We can see some stainless steel clips at the top of the module there. There's another one here. We can see some outdoor rated plastic zip ties used on the equipment grounding conductor there. Very nicely done. That's not going to have any issues moving forward. Let's talk about our roof mounts. You know, back in the day, we didn't have nice flashings like we see in this picture. All we had was the L-foot, and we did what we at SEI like to call goop in a prayer. We used some sealant, just put it on the underside. We had to use a piece of step flashing above the sealant to direct water around the L-foot, and it worked okay, but that's not acceptable these days. We can't just rely on sealant to secure that penetration. We have all kinds of different flashings. Any kind of roof type that you're going to use, there's a flashing that someone makes for that roof. So there's really no excuse not to use a flashing when installing a system. We need to use the right flashing for the right roof. We need to make sure that that is compatible and appropriate. We also need to take a look at the roofing and make sure that it is not worn out, or make sure it's not damaged, and assess that roof condition before we put the system in. Ballasted systems add additional weight, so we need to look at how that is going to affect the structure. We also need to see if it's a membrane roof, same as any other roof type. We need to make sure that it's going to, in good condition, that it's going to last. We need to see if that is going to shed dirt and snow, and we'll see some pictures of that coming up. And we can't do hybrid systems, and what we mean by that are ballast mounted systems where we use weight to hold the array down that are also mechanically attached to the building. Granted, the ballast allows you to do significantly fewer mechanical attachments, so that's good, but we may need to do that. Here's some pictures of some different types of flashings. The one in the top right-hand photo is an excellently installed flashing, and that's perfect. It looks like this is a new roofing installation. So they were able to put that flashing in most likely before they put the shingles in. But either way, it's not hard to retrofit these flashings into an existing asphalt shingle roof. On the left-hand side, we see a ballast mounted system. There's a couple things I want to point out here. This is a slip sheet underneath the tray for the ballast and underneath the mounting foot. So that is simply the same membrane that the roof is made out of, put between the actual roof and the racking. And this allows the racking to move a little bit on top of the roof, and the racking itself won't be digging into the roofing. The slip sheet prevents that racking from damaging the roof. This ballast is also, it's really hard to see in this picture, but there's wire that goes up and over this ballast, securing the ballast to the pan. That is an excellent installation. We also need to make sure that we get the right type of ballast. We can see this piece of ballast block down here is on our lab yard in Paonia, Colorado, and it is completely disintegrated. Um, that happens if you don't get the right kind of concrete. Read the manual for the racking manufacturer. They will specify the type of concrete that block needs to be made out of. Don't just go down to the hardware store and buy the cheapest block you can get, because you will be up on that roof in 5 or 10 years shoveling gravel off the roof and reinstalling all that ballast block. And what's going to happen, let's say this ballast up here disintegrates, what's going to happen with all those little rocks? They're going to get underneath the slip sheet, they're going to get underneath the rack, they're going to get underneath the foot over here, and that's just going to dig a hole in the roof. And then you're not only going to be replacing the ballast, you're going to be replacing the roof too. And nobody wants to do that. So in this top center picture, that's Goop and a prayer. It's just an elephant with some caulk on it and hope that doesn't leak. Kind of same thing down here with this metal roof. In both these pictures are metal roof down here. This is not the appropriate mounting bracket for either one of these roof types. They make lots of different options for all kinds of different metal roofings, so there's no excuse for not using the right type of racking there. Now, this is a plumbing vent, so it's not specifically a PV system, but this OD type flashing boot has cracked, and we can see that's no longer weatherproof there. So we need to make sure that whatever materials we're using are rated for the environment and are going to last as long as the system is going to last. Here's some more examples of racking gone wrong. We'll start at the top here. The span between these mounting foot, there's one mounting foot here, there's one mounting foot there. I can guarantee that exceeds the maximum span of this racking manufacturer. That's going to be a violation of the installation manual. I also don't understand, why is this one in the center short when these other ones are long? So where's the mounting bracket for this one? Is it underneath the array? And then what's the cantilever on that one there? I can guarantee it's going to violate what the manufacturer's requirements are. Here we have a bracket. The little clamp that goes into the rack channel here is not installed properly. So it's twisted sideways. It should be 90 degrees from that. So that's actually not securing that module down. This will fail. This end clamp will come out. It'll cause this module to fail, which will loosen the mid clamp on the next module, which will cause that module to fail. And you have what's called a zipper effect, where that whole row of modules may come out of the rack just because this one clamp wasn't installed properly. In the center picture, we have two modules butted up against each other. This is a common installation error. The module manufacturer's installation instructions and the racking manufacturer's instructions are going to say that there needs to be a space between those modules. And that's to allow for expansion and contraction. And usually it doesn't need to be much, half an inch or so. A module mid clamps worth of space would be enough to allow that module to expand and contract. If it doesn't have space to expand and contract, it can actually shatter the glass of the module. So we really need to have that space there. In the bottom right, we can see an end clamp that is not installed properly. There's a gap between the clamp and the edge of the module. The module should be butted right up against this edge here. You know, the sad part is that this is an S5 clamp directly mounted to the standing seam, and you can just undo a little set screw on the back side of this clamp and push it in. So why they didn't just do that in the first place, who knows? They were lazy or rushing and didn't spend the time to take care of that. Soiling can be an issue. We've got a couple different examples here. Dirt on the top, bird leavings at the bottom left there, and snow on the bottom right. Is this an issue? This bottom one with the bird poop all over the array. Yeah, I'd say that's a pretty big issue. I believe they lost somewhere about 30 to 40% of production on this system due to the soiling there. This dirt in the top, is it going to rain next week? Does this need to be cleaned? You need to do a financial analysis to see what's the cost to clean this array versus the increase in production. Now, snow is something that you really need to think about. The downside of this system is you're going to lose some production, but the time of the year where you're going to lose production is the time of the year where you're not making a lot to begin with because you don't have a lot of irradiance. So you might not be losing as much as you would think. Again, you have to do a financial analysis and see what is the increase in production versus the cost to remove the snow, and does it justify that expense. Expansion and contraction can be a really serious issue. It has actually led to several fires in the PV industry. So when we have conduit on the rooftop, that's going to expand and contract depending on the temperature. So we need to make sure that we have the proper installation technique to allow for that expansion contraction. So we have the proper wire bending radius. We're avoiding sharp edges of racking and modules. If we have long runs, are we going to put more junction boxes in? Are we going to put expansion fittings? Are we going to have bends in the conduit to allow for expansion and contraction? NEC 307B requires expansion fittings and expansion fittings if there's a joint in the building. This is especially important on commercial buildings. A lot of times they'll have expansion joints in the actual building. So we also need to have accommodations for expansion and contraction at that same joint. Also, your roof standoffs on low slope or flat commercial roofs should float on the roof. They shouldn't be directly attached to the roof, and that will allow the conduit to move around a little bit. Here's some examples of metal expansion fittings. They are required anytime thermal expansion is going to be greater than 6 millimeters or 1/4 of an inch. We need to follow the instructions, RTFM, and we're going to base that installation on the temperature at the time we install it. Metal conduit, the expansion fittings must also maintain the bonding of the conduit. We can see on that right picture, we have external bonding on that expansion fitting. We've got that braided cable there, and the one on the left has bonding internally to that expansion fitting. So bonding in both of those cases. Here's an interesting system. My co-worker Roger Williams and I were doing a training in Alaska and rolled up on this system at the local college. It was a ground-mounted system, and this was the DC disconnect going into the building. That metal conduit coming up from the ground is what ran over to the pole mount, and then the little LB at the left-hand side there goes into the building. And I walked up to this and said, "Hey, Roger, look, there's no expansion fitting on this metal conduit." And then I looked underneath and saw that that metal conduit had pushed up out of the ground about 6 inches into the disconnect. So that disconnect was basically completely destroyed. Luckily, well, unfortunately, I should say, the system had been decommissioned because the local kids had thrown a bunch of rocks at the array. So there were several shattered modules. So you can see his disconnect is off, but this disconnect is severely damaged. I would be willing to guess that this conduit is pushing up into the underside of the terminals that disconnect. Unfortunately, I had this giant padlock on it, so he couldn't get into to take pictures of the inside, but I would definitely do not turn that on. I would be willing to bet you got some ground faults or arc faults in that box for sure. Here we've got an equipment grounding conductor. Again, my pet peeve, which you've heard so much before, green THWN2, not sunlight resistant. Here's a white zip tie. That's not going to last more than about 6 months there. And this is pulled so tight, there's absolutely no room for expansion and contraction here. They use the right lug, so that's a plus. Here, they're missing a whole bunch of the strands of the wires are missing on that lug there. So that is not code compliant. And again, that's pulled so darn tight, there's no room for expansion and contraction there. This mounting bracket also not proper for this type of metal roof, so they need to get the right type of bracket for that roof. Here's the impact of expansion and contraction in a couple different situations. This junction box up here is a combiner disconnect together in one box, has moved, this conduit has pushed the combiner box back and has caused this to move. You can see this is floating on there, so that's good. You got some room for movement there, but had some expansion contraction issues on this conduit for sure. This conduit pulled right out of the junction box. So that's not good. Eventually that will wear the insulation of this wire away. It's not going to cause a ground fault because it's a PVC conduit, but it may cause an arc fault and you may burn up all these PV source circuits in there. This conduit just looks like spaghetti. So lots of expansion and contraction issues going there. And here the wire's just laying on the roof between the modules. So that's not acceptable. It needs to be underneath the array or in some kind of conduit there. Well, thank you for joining me for this 1-hour session on best practices for PV installation. I hope you got something good out of it. For more training, you can check out our website, solarenergy.org. I'm sure we have a new session of online courses starting soon. We also have the on-demand continuing education classes that are always available. And again, you get a $50 discount using that code that was at the beginning of the presentation. So thank you very much and have a great day.
Hello, I'm Brian Mahalik from Solar Energy International. Welcome to this presentation on the 2020 National Electrical Code and PV and energy storage systems. This presentation is part of North America Smart Energy Week. You can see some of the sponsors and organizations responsible for bringing this to you. I myself represent Solar Energy International. Since 1991, we've been providing training to individuals, organizations, and communities all over the planet, and we have over 75,000 alumni around the globe. You may have taken an SEI class before. Welcome back. Maybe this is your first one. Well, welcome here. And you're very likely that you may work with somebody that's taken a class. So if you have any questions about what we can offer you as an individual or your company or organization, please visit us at solarenergy.org. As I mentioned, my name is Brian Mahalik. I am SEI class of 2002. I'm an instructor and curriculum developer for them, and I'm also a senior technical advisor for SEI Professional Services. I'm an ABCEP certified PV installation professional since 2008, and I'm also a member of National Electrical Code CMP4. Codemaking Panel 4 has responsibility for many of the articles that we'll be talking about throughout the rest of this presentation. So let's talk briefly about SEI and the National Electrical Code. We've been active participants in it for numerous cycles now, and one way we do that is through the PV Industry Forum, sponsored by SEIA, a trade organization. This is a way to bring various stakeholders across the industry together, develop consensus proposals that are then submitted to the codemaking panel for consideration in the next codemaking cycle. As I mentioned, I am a member of CMP4. I'm the alternate. Rebecca Wharton-Wren is the principal. We were first voting members in the 2020 cycle, and we are beginning to work on the next version, 2023, now. Our goal really is to represent our alumni, system designers, installers, people that have taken our classes that maybe don't have another avenue to participate in the codemaking process. Now, it is a public process, but we are really looking out for the best interests of the industry at large and trying to really speak for installers and designers who may not have the weight behind them that comes with trade organizations or being part of a specific manufacturer or some other way involved in the industry. So we're not beholden to any specific product or specific technology or way of doing things. We just want systems to be safe and reliable. And really, we also love the NEC, and it's a passion of ours, and we're glad and proud to be members of the process. So briefly, I do want to say, hey, you always got to be thinking about the next code cycle. You know, many of you may be in an area where 2020 is just being adopted, or maybe it was a year ago or fairly recently, or maybe it won't be for a while. Regardless, the next version is starting to be worked on. It's underway. 2023 is coming fast. Maybe some of us say, hey, in a 2020 world, it can't come fast enough, but there are some deadlines that have already passed. So you want to get involved. It's a public process. You can find out more information by going to nfpa.org and looking under NFPA 70, the National Electrical Code, for the next edition and more information. Now, it's called the 2022 revision cycle. The output will be the 2023 version of the code, and the first deadline for initial public inputs has already passed, September 10th, 2020. That one's gone. The next thing that'll happen is the CMP will meet, we'll go over the proposals that are submitted, and eventually this will result in the first draft coming out in July of next year. Once that first draft is out, then hey, it's back open to the public. That's your time to look at it, make comments on the first draft, and then a second draft will come out in March of 2022 with the 2023 NEC being published sometime in September of 2022. Before we really dive into some of the key changes in regards to PV and energy storage systems, let's just make sure we have a good understanding of what the purpose of the NEC really is. Section 90.1, practical safeguarding, 90.1a, safeguarding of persons or properties from hazards. This code is not a design specification or an instruction manual for untrained persons. You know, you can't pick it up and read it cover from cover and then say, hey, I know how to design and install systems. That's not the way it works. Also, fundamentally, is that if you follow the code and you meet the requirements, you will result in a system that is essentially free from hazard, but it might not be efficient, it might not be convenient, it might not be adequate for good service or future expansion. The code is a minimum. It's a minimum. Now, yeah, hey, these are the minimum standards for preventing hazards. PV systems, which have a expected life of multiple decades and are outside in harsh conditions, well, doing it better may make sense sometimes. So we always want to keep that in mind. Code is the minimum. We can go above and beyond. Of course, we need to balance cost and practicality when we make those decisions. So we're going to start at the beginning and kind of work our way through here in numerical order, really highlighting some of the key changes. First off, we'll start off in Article 100, definitions. There's lots of new stuff going on in here. Some of them are things like island mode. So this could be permanently and standalone, right? Not connected to a primary power source, off grid, we might call it. Or it could be a system that sometimes operates in parallel with the utility grid, but can disconnect and operate in standalone mode, also now known as island mode. 2020 also has a modified version of the PV system definition, specifying that it's all equipment up to and including the PV system disconnect. And what we also see is that a lot of definitions have moved into Article 100, to the front of the book. So Article 705, power production equipment. A bunch of definitions in Article 690 that you can see on the slide here. These have relocated to Article 100 because they are used in multiple locations consistently, multiple articles throughout the NEC. Now, I would recommend that if you want to take a moment, get out your code book, review some of these definitions. If you're not familiar with them, we will be utilizing them, this terminology, various locations as we work our way through this presentation. New in 2020 in 690.2 is an AC module system. So this is an assembly of AC modules, wiring methods, materials, and sub-assemblies that are evaluated, identified, and defined as a system, right? So an array of AC modules is one part of an AC module system, but by no means can we say, hey, I've got some AC modules, I put them together, that's an AC module system, right? It's not evaluated and identified as a system, right? So we're talking about racking and wiring and other parts and pieces that go together to make the system up. Those can now be classified as an AC module system. So this seems pretty straightforward, but when you get down into the weeds of it, the question comes up, hey, why would you even want to classify something as an AC module system? Right now, to some degree, the manufacturers have some leeway in defining what is included and not included in the boundaries of what an AC module system is. So some of the benefits may be available to you and some of them may not, depending on where they laid those boundaries. And in a lot of ways, this kind of gives us a stepping stone to a future of what we might want to call plug and play, right? Kind of moving from the string inverters to module level electronics, which we've kind of seen happen in a lot of rooftop applications in particular. And this is really kind of building the code out to allow it to grow and move in that direction, or in that direction in terms of at least being an opportunity for the way we design and install systems as we have new products in the future. Also new in 2020, definition of electronic power converter, EPC we'll call it, not engineering, procurement, and construction, EPC, electronic power converter. And hey, the definition is pretty obvious. It's power electronics that converts electrical power from one form into another. It may be changing current, voltage, probably both. And these are things like inverters, DC to DC converters, electronic charge controllers, equipment that we're very familiar with and used to. We're now grouping it together all as electronic power converters because they have some similarities, right? They have current limited capabilities based on their continuous rated power. It can do what it can do. It can take what it can take and can put out what it can put out. That may be different than other types of circuits, so we want to group them together so that we can apply rules similarly to these various types of EPCs. Now you'll notice throughout 690 and 7. Hello, I'm Brian Mahalik from Solar Energy International. Welcome to this presentation on the 2020 National Electrical Code and PV and energy storage systems. This presentation is part of North America Smart Energy Week. You can see some of the sponsors and organizations responsible for bringing this to you. I myself represent Solar Energy International. Since 1991, we've been providing training to individuals, organizations, and communities all over the planet, and we have over 75,000 alumni around the globe. You may have taken an SEI class before. Welcome back. Maybe this is your first one. Well, welcome here. And you're very likely that you may work with somebody that's taken a class. So if you have any questions about what we can offer you as an individual or your company or organization, please visit us at solarenergy.org. As I mentioned, my name is Brian Mahalik. I am SEI class of 2002. I'm an instructor and curriculum developer for them, and I'm also a senior technical advisor for SEI Professional Services. I'm an ABCEP certified PV installation professional since 2008, and I'm also a member of National Electrical Code CMP4. Codemaking Panel 4 has responsibility for many of the articles that we'll be talking about throughout the rest of this presentation. So let's talk briefly about SEI and the National Electrical Code. We've been active participants in it for numerous cycles now, and one way we do that is through the PV Industry Forum, sponsored by SEIA, a trade organization. This is a way to bring various stakeholders across the industry together, develop consensus proposals that are then submitted to the codemaking panel for consideration in the next codemaking cycle. As I mentioned, I am a member of CMP4. I'm the alternate. Rebecca Wharton-Wren is the principal. We were first voting members in the 2020 cycle, and we are beginning to work on the next version, 2023, now. Our goal really is to represent our alumni, system designers, installers, people that have taken our classes that maybe don't have another avenue to participate in the codemaking process. Now, it is a public process, but we are really looking out for the best interests of the industry at large and trying to really speak for installers and designers who may not have the weight behind them that comes with trade organizations or being part of a specific manufacturer or some other way involved in the industry. So we're not beholden to any specific product or specific technology or way of doing things. We just want systems to be safe and reliable. And really, we also love the NEC, and it's a passion of ours, and we're glad and proud to be members of the process. So briefly, I do want to say, hey, you always got to be thinking about the next code cycle. You know, many of you may be in an area where 2020 is just being adopted, or maybe it was a year ago or fairly recently, or maybe it won't be for a while. Regardless, the next version is starting to be worked on. It's underway. 2023 is coming fast. Maybe some of us say, hey, in a 2020 world, it can't come fast enough, but there are some some deadlines that have already passed. So you want to get involved. It's a public process. You can find out more information by going to nfpa.org and looking under NFPA 70, the National Electrical Code, for the next edition and more information. Now, it's called the 2022 revision cycle. The output will be the 2023 version of the code. And the first deadline for initial public inputs has already passed, September 10th, 2020. That one's gone. The next thing that'll happen is the CMP will meet, we'll go over the proposals that are submitted, and eventually this will result in the first draft coming out in July of next year. Once that first draft is out, then hey, it's back open to the public. That's your time to look at it, make comments on the first draft, and then a second draft will come out in March of 2022 with the 2023 NEC being published sometime in September of 2022. Before we really dive into some of the key changes in regards to PV and energy storage systems, let's just make sure we have a good understanding of what the purpose of the NEC really is. Section 90.1, practical safeguarding, 90.1a, safeguarding of persons or properties from hazards. This code is not a design specification or an instruction manual for untrained persons. You know, you can't pick it up and read it cover from cover and then say, hey, I know how to design and install systems. That's not the way it works. Also, fundamentally, is that if you follow the code and you meet the requirements, you will result in a system that is essentially free from hazard, but it might not be efficient, it might not be convenient, it might not be adequate for good service or future expansion. The code is a minimum. It's a minimum. Now, yeah, hey, these are the minimum standards for preventing hazards. PV systems, which have a expected life of multiple decades and are outside in harsh conditions, well, doing it better may make sense sometimes. So we always want to keep that in mind. Code is the minimum. We can go above and beyond. Of course, we need to balance cost and practicality when we make those decisions. So we're going to start at the beginning and kind of work our way through here in numerical order, really highlighting some of the key changes. First off, we'll start off in Article 100, definitions. There's lots of new stuff going on in here. Some of them are things like island mode. So this could be permanently and standalone, right? Not connected to a primary power source, off-grid, we might call it. Or it could be a system that sometimes operates in parallel with the utility grid, but can disconnect and operate in standalone mode, also now known as island mode. 2020 also has a modified version of the PV system definition, specifying that it's all equipment up to and including the PV system disconnect. And what we also see is that a lot of definitions have moved into Article 100, to the front of the book. So Article 705, power production equipment, a bunch of definitions in Article 690 that you can see on the slide here. These have relocated to Article 100 because they are used in multiple locations consistently, multiple articles throughout the NEC. Now, I would recommend that if you want to take a moment, get out your code book, review some of these definitions. If you're not familiar with them, we will be utilizing them, this terminology, various locations as we work our way through this presentation. New in 2020 in 690.2 is an AC module system. So this is an assembly of AC modules, wiring methods, materials, and sub-assemblies that are evaluated, identified, and defined as a system, right? So an array of AC modules is one part of an AC module system, but by no means can we say, hey, I've got some AC modules, I put them together, that's an AC module system, right? It's not evaluated and identified as a system. Right, so we're talking about racking and wiring and other parts and pieces that go together to make the system up. Those can now be classified as an AC module system. So this seems pretty straightforward, but when you get down into the weeds of it, the question comes up, hey, why would you even want to classify something as an AC module system? Right now, to some degree, the manufacturers have some leeway in defining what is included and not included in the boundaries of what an AC module system is. So some of the benefits may be available to you and some of them may not, depending on where they laid those boundaries. And in a lot of ways, this kind of gives us a stepping stone to a future of what we might want to call plug and play, right? Kind of moving from the string inverters to module level electronics, which we've kind of seen happen in a lot of rooftop applications in particular. And this is really kind of building the code out to allow it to grow and move in that direction, or in that direction in terms of at least being an opportunity for the way we design and install systems as we have new products in the future. Also new in 2020, definition of electronic power converter, EPC we'll call it, not engineering, procurement, and construction, EPC, electronic power converter. And hey, the definition is pretty obvious. It's power electronics that converts electrical power from one form into another. It may be changing current, voltage, probably both. And these are things like inverters, DC to DC converters, electronic charge controllers, equipment that we're very familiar with and used to. We're now grouping it together all as electronic power converters because they have some similarities, right? They have current limited capabilities based on their continuous rated power. It can do what it can do. It can take what it can take and can put out what it can put out. That may be different than other types of circuits, so we want to group them together so that we can apply rules similarly to these various types of EPCs. Now you'll notice throughout 690 and 705 and other places, many times inverter or charge controller has changed to electronic power converter, but not always. So your mileage is going to vary on that, and it depends. Hopefully, as we continue to move forward with the next cycle, we'll kind of clean that up more and more as we go. Okay, 690.4F, EPCs, electronic power converters, we just talked about, in non-readily accessible locations. This moved from 705.70, where it was previously located, into 690.4. Now, I'm not entirely sure this was the best idea because if you think about it, an EPC doesn't necessarily have to have a PV system connected to it. So maybe 705 would have been a good place. Maybe it needs to be in both. We'll see. But in general, it's kind of really gives us the same allowances. We can put EPCs in non-readily accessible areas like a roof or elevated on a carport. We've got to follow the requirements in 690.15 for disconnects, right? Plug connectors might meet those requirements for MLPE, module level power electronics. Roof-mounted string inverter is going to have the same equipment disconnect requirements as ones that are readily accessible. And the PV system disconnect has to be readily accessible. So the EPCs don't have to be, the equipment disconnects, right? They don't have to be, they need to be located with the EPC, but we do have to have a readily accessible PV system disconnect. Circuits connected to the input of electronic power converters, EPC. So 690.8A2, new in 2020. This allows for sizing conductor ampacity so that it is less than the maximum circuit current in some scenarios. Now, normally we would not have been able to do that, right? Maximum circuit current, we got to have a conductor that can handle that. Well, there are certain scenarios where that is no longer the case. So if we have circuits with overcurrent protection where that OCPD, that overcurrent protection device, is less than or equal to the conductor ampacity, okay, so that means the OCPD is going to protect the conductor, then we can use the maximum circuit current, which is the equivalent of the rated input current of the EPC that circuit's connected to. So it kind of makes sense. We're saying, hey, we've got some sort of fuse or breaker protecting this conductor, and the conductor is only ever going to carry a certain amount of current because the converter it's connected to can only take a certain amount of current. So this allows for smaller conductors in some cases, especially where we have, for instance, high array current to EPC input current ratios. So here's an example. PV output circuit, 67 amps. Normally we would say maximum circuit current, multiply that by 1.25, gives us 83.75 amps. But let's say that circuit is connected to a charge controller that can only take in 60 amps. If there's more power available or more current, it's going to modulate the IV curve and move to a different combination of current and voltage, or so that it limits itself to that 60 amps of input. And the wire is thus only ever going to see 60 amps of input. Now, that wire is also protected with an OCPD that's rated at its overcurrent protection level or its ampacity level, so it is protected by that as well. Now, 690.9a says, hey, if you do size conductors in this way, you have to use overcurrent protection devices on those circuits. So it's going to be there, it's required to be there by 690.9a. But this is a way really to say, hey, this is what's going to really happen with the system. The wire's protected by the OCPD, but the wire is never going to carry more than what the EPC is going to take in, so let's use that as our circuit sizing. Allows us to right-size conductors and not essentially oversize them for conditions that are never going to actually happen. We're going to spring ahead just a little bit because this sort of ties in. We want to look at some conductor ampacity tables, 690.31AA and AB. These changed pretty significantly in 2020, whereas they used to give us correction factors that were different from those in Article 310. They're now related to different conductors altogether. Okay, so these are specific conductors with insulation ratings up to 2,000 volts. There are 105 degrees C rated insulation categories and 125 degrees C. You can see the various conductor types that go along with those insulation ratings on the slide there. And 690.31AA gives us temperature correction factors for these conductors, so based on the temperature. And it all 690.31AB, which is on the slide here, gives us the ampacity for those various conductors. So if we're using these types of conductors, which have these higher insulation ratings, we can use the ampacities and the temperature correction factors in these tables. Now, as you would expect, higher rated insulation is going to mean higher ampacity for the same size conductor. So that's the advantage here. Now, you may or may not encounter a lot of these conductor types out there, but if they're available to you, it's a way to potentially reduce wire size while still designing and installing a safe system. Okay, let's jump back now to 690.9A, circuits and equipment. Must be protected against overcurrents. And there's really 3 different protection scenarios that we'll go into more detail on in the next several slides. First would be the ampacity of the conductor, or the rating of the component is greater than or equal to the maximum current. Well, that means there is no overcurrent. It can handle what's available. The next scenario we'll want to consider is where the conductor ampacity is greater than or equal to the maximum current on one end of the conductor, but on the other end, it's not. We'll look at those scenarios here in a minute. And then the final is other, and we'll see that there are now lots of other options to consider in 690.9a. Okay, so significant changes in 2020. Let's start off with 690.9a1, overcurrent protection not required. So conductor ampacity greater than or equal to the maximum circuit current. There is no source of overcurrent for those conductors as a result. But we also have to make sure that the current from all sources is less than or equal to the maximum overcurrent protection device size. Right, so as specified by the module, for instance, it has a maximum OCPD size, or it may be that it is specified for a charge controller or DC to DC converter or inverter. So those two conditions, as long as they're met, then we don't have to have overcurrent protection. Okay, now the circuit current we're going to calculate based on 690.8A1, so that would be short circuit current times 1.25, or the rated current of the EPC times 1.25. So an example would be a PV module connected to a DC to DC converter. Now we are assuming, in this case, we can't backfeed the PV module from the DC to DC converter. That's something we have to verify with the manufacturer of the DC to DC converter. Another example would be two PV source circuits connected in parallel on a single maximum power point tracker. That maximum power point tracker is isolated from other inputs to the inverter. It is not capable of backfeeding. Again, we'll verify that with the manufacturer. There is no source of overcurrent in that scenario as well. So we commonly see that. Inverse string inverters with multiple maximum power point tracking inputs, 2 strings per input, no DC fusing required. Okay, 690.9A2, overcurrent protection required on one end. So here's the scenario. Conductor connected to a current limited supply on one end. Could be a PV module. Could be the output of an electronic power converter. It's limited to what its rated output current is. It's a circuit where the ampacity is greater than or equal to whatever that current limited supply is. So the PV module or the output of the electronic power converter. And that circuit is connected to a source with current that is greater than the conductor ampacity. Okay, so those are the 3 conditions we have in 690.9A2. And the result is we have to locate overcurrent protection on the end of the circuit connected to the higher current source. You know, this is really kind of a long-winded way of saying wherever we have stuff coming together in parallel, we're going to need to have overcurrent protection. A combiner box, multiple PV source circuits coming together. We then have fusing on them to protect them from the parallel output of all the source circuits in there. Or an inverter AC combiner, the breaker on the output of the AC, protecting it from the higher current source being the grid. Okay, so that is 690.9A2. Where we really have some big changes in 2020 is in 690.9A3, other circuits. And these would be circuits that don't comply with A1 or A2. And now we have 4 types of other, okay? And these would be, well, I'm not going to read through all these here for you, but conductors less than or equal to 10 feet on, not on a building, protected from overcurrent on one end. Conductors less than or equal to 10 feet in a building and in raceway or metal clad cable, protected from overcurrent on one end. Now, if you think about it, that's kind of how like service entrance conductors are protected, right? We have the utility grid coming into the service, and we have a breaker there limiting the current to the conductors downstream from that on the customer side of the service. Right? The wires coming to that overcurrent protection are subject to the full current from the grid, whatever it would take to make the overcurrent protection in the supplying transformer open, essentially. So it's a very similar scenario to that. Now, some examples would be a PV output circuit that's less than or equal to 10 feet long. We may have overcurrent protection in the central inverter, where it is connected in parallel with other PV output circuits, but we don't have to have them in the DC combiner box on that output, okay? Another example would be an inverter output circuit to a transformer. We could have overcurrent protection in the inverter, but we don't have to have it in the transformer, okay? So these are just different ways to provide adequate protection, provided we meet the conditions in one or two, okay? So there's a distance requirement there, and it's either in a building, in which case it's gonna need to be in a raceway or a metal clad cable, or it's not in a building. So these are very common scenarios that we have really utilized in many instances historically, and this is really codifying it as a way that we can in fact safely design and install systems. Now, there are some others, 690.9A3. We could protect a conductor from overcurrent on both ends, right? It's the Cadillac, the ultimate in overcurrent protection. It comes at a cost because, well, now we have overcurrent protection on both sides where we may not need to do that, but there may be other advantages associated with that. 690.9A4, conductors not in or on buildings are also allowed to be protected from overcurrent on only one end, provided a list of 4 conditions are met. And I'm really not going to read through all of these for you now, but this would allow us to only have overcurrent protection on a single end, but these are conductors not on buildings. So we don't have a distance requirement anymore like we did in A1, but we do have numerous other requirements that must be met, which are pretty typical of requirements we see in other locations in the code in regards to service conductors, for instance. All right, we're going to jump ahead. 690.31C, cables, type PV wire and type DG, distributed generation cable, shall be listed. So UL 4703 is the standard for PV wire. That's been in the code for several cycles now. New in 2020 is the reference to UL 3003 distributed generation cables. These are often multi-conductor jacketed cables. Here's an example used with an N-phase system. And there's a variety of applications out there, and expect to see more and more of these conductors becoming used in various applications, both on the AC and DC side of systems. Single conductor cable. We've got some changes here. Now, they have to be marked sunlight resistant and USE2 and RHW-2 or PV wire. Okay, so we've basically built up on the USE2 or PV wire option. Now that's sunlight resistant USE2 and RHW-2, or just go with PV wire. Here's a big change. Support and secure exposed cables every 24 inches. Okay, using cable ties, straps, hangers, similar fittings, listed and identified for securement and support in outdoor locations. So clear minimum wire management requirements in 2020. Love them, hate them, you got to do them. At least we have guidance now as to how often those conductors need to be secured and supported. Now, there's an exception, large-scale PV, Article 691. We're not going to talk about that much because there wasn't many changes, but there's an exception as long as the securing and supporting method is defined in the engineer design, the 24-inch requirement does not apply. 690.31c3, multi-conductor jacketed cables. An example, as I already mentioned, type DG cable. There's lots of new stuff here in 31c3. Follow the instructions if it's part of a listed assembly. Of course, we're always going to do that. We RTFM, read the free manual that comes with the equipment you're using. But if it's not, if we're using a spool of this multi-conductor jacketed cable, for instance, whatever it may be, then install it in raceways if on or in a building and not on the rooftop. If it's not in a raceway, then we have to meet all the following. It's got to be sunlight resistant if outdoors and exposed, protected and guarded if exposed to physical damage, follow the surface of support structures, secured every 24 feet, within 24 inches of mating connectors or connectors or enclosures, and mark direct burial if buried. So nothing really surprising there. It's just being called out now for the first time in Article 690, specific to these types of conductors. 690.31d2, marking and labeling DC circuits on or in buildings. Okay, so not on ground-mounted systems, on or in buildings, DC circuits, not inverter circuits, DC circuits on or in buildings. Hey, if you arrange it and locate our conductors that are our circuits so that the purpose is evident, then you don't have to mark or label it. If it's not obvious, then yeah, we have to mark or label exposed raceways, cable trays, or other wiring methods, pull boxes and junction boxes, conduit bodies with available unused openings. That should be familiar language, but, and the label familiar as well. The change here is if it's obvious, if you've got a piece of conduit running into a disconnect that's clearly marked as a DC disconnect and it goes to an inverter and then there's AC coming out of it, and it's obvious what's going on here. Now, of course, that's going to be open to some interpretation potentially, but this could help us cut down on some of the, what I think of as chronic over-labeling in our systems, where warning photovoltaic power sources just plastered all over the place, AC circuits, DC circuits just everywhere. Doesn't look great. We don't necessarily need it, and this is a new allowance in 2020. Now, these do have to be visible after installation, suitable for the environment every 10 feet. If there's separation by a partition, ceiling, or floor, you got to mark it on both sides. And we are specifically required to use 3/8-inch all-cap white letters on a reflective red background, because the idea being this is something that we're really going to want to indicate to a first responder or a firefighter that could be on the scene. 690.31f, wiring methods and mounting for a roof-mounted systems. So back on the roof specifically here. This is new in 2020, and the allowance is for PV array mounting systems that are different or use means other than those prescribed in 110.13. So basically, this is an allowance to use ballasted arrays, something we've done for years and years, but something that if you looked at the requirements of 110.13, maybe really didn't meet the letter of the law. So this is a big improvement and enhancement, legitimizing, if you will, ballasted arrays. Now, we do have to use wiring methods that allow for expected movement of the array. And there's an informational note that says, hey, yeah, expected movement, that's usually part of the structural calculations. If there is expected movement, if it's seismic related, if there's vibrations, whatever it may be, that's going to be encompassed in the structural design of the system. And we need our wiring systems to have the flexibility or other means to allow for that expected movement. Lots of changes, big changes in regards to connectors. 690.33c, mating connectors must be latching or locking. Readily accessible mating connectors, if circuits are over 30 volts DC or 15 volts AC, you got to have a tool to open them. And here's the big one, where mating connectors are not of the identical type and brand, they must be listed and identified for intermatability. And where are we going to find that? We're going to find it from the manufacturer. So they've got to be tested and listed to work together if they're not the same make and model. So intermatability. I wasn't 100% clear that that was a word before 2020, but lo and behold it is, and it's a requirement when we use our plug connectors, right? Because we've historically done a bad job on this, right? We connect brand X to brand Y, and maybe there's some brand Z's sprinkled in there for good measure, modules to the module level power electronics with mix and match, and that can lead to failures. We're using products that aren't listed to mate together. That can lead to liability, and it's something now that we are no longer allowed to do. So either use the same make and model or find ones that are tested and listed together. That's a little bit harder. 69041B, ground fault protection. This is to reduce fire hazards. The new requirement in 2020 is that this is for PV system DC circuits that are greater than 8 amps or 30 volts. So that is a change in 2020. Also an informational note saying, hey, not all power electronics include ground fault protection. We know that most of our grid direct inverters do. Some of our charge controllers do. Sometimes it's going to be a separate external device that we'll have to have as part of the system when we have PV system DC circuits greater than 8 amps or 30 volts. So it's not required for solidly grounded systems where we have less than 2 modules in parallel and where the DC is not in or on a building. So that's a pretty small number of overall systems out there. And the device has to be listed for PV ground fault protection, and it's got to be able to detect faults in all DC conductors, including those that are functionally grounded. Okay, so that change came into the code a couple cycles ago and has really made our ground fault protection much better. Ground fault protection also has to isolate faulted circuits by either automatically disconnecting the current conductors or shutting down the inverter or charge controller and isolating the DC circuit from the ground reference if it's functionally grounded. So in many ways, those are manufacturer requirements. You use listed ground fault protection, it's going to do one of these two things. New in 2020 is the indication of faults in 69041B3 must be indicated at a readily accessible location, and examples include, hey, a remote indicator or a display or a monitor, an alarm system, a web-based service. It could be on the inverter itself. It could be I'm looking at my phone. There's a lot of different ways to indicate that ground fault. This is helpful for instance, inverters that are mounted in non-readily accessible locations. Well, the monitor or data system can be the indicator of the ground fault, not hindering my ability to put that inverter, for instance, high up on a carport, for instance. 69043D. So this is a big 2020 change modifying the requirement in 250.97. So 250.97 only applies to solidly grounded PV system circuits operating above 250 volts to ground. Now, what that effectively does is eliminate nearly all DC circuits, right? Our PV systems tend to be functionally grounded. The allowance for solidly grounded systems is pretty narrow. We don't have a lot of those out there anymore. So this means we don't really need to do the bonding for eccentric or concentric knockouts that we used to have to do and is shown on the slide here. That's an AC example, as you can tell by the color coding of the wires there, but that's the bonding bushing, right? We don't have to bond that conduit in accordance with 250.97 any longer. Now, it is still going to be required for solidly grounded AC circuits, for instance, 480 volt AC or above, where it's a solidly grounded system, but no longer required on the DC side when we're above 250 volts to ground. Unless they're solidly grounded. Sizing the equipment grounding conductor for PV system circuits, another big 2020 change. Increases in EGC size to address voltage drop are not required on the AC or DC side of the system. Normally, 250.122b would say, hey, if you made your wires bigger to deal with voltage drop, you got to make the equipment grounding conductor bigger proportionally as well. We no longer are required to do that. And the logic here is that, hey, if the wires are bigger because of voltage drop considerations, we reduce the impedance in a fault condition. A large part of the circuit already has much less voltage drop as part of it, so we're not going to decrease the likelihood of overcurrent protection, seeing the amount of current that's required to trip it. So this is a big change in 2020, no longer needing to upsize those equipment grounding conductors. Also new in 2020 or some changes in the labeling requirement in 690.53, the DC PV circuit labeling. We have to label with the highest maximum DC voltage that we calculate in accordance with 690.7. It's got to be at a permanently readily visible location. And we say highest because, hey, there could be more than one, right? Maybe we have an inverter with multiple maximum power point tracking inputs, and one of the inputs has 13 modules in series, the other has 15. Different highest maximum DC voltages. We don't got to label both. We label the highest because that's going to inform us on the voltage that we're going to need to consider in terms of selecting PPE when working on the system. The lower one, hey, if I'm geared up for the higher one, I'm going to be fine for the lower one as well. Not a consideration, just label it for that higher value. Now we have to provide this label on at least one of the following locations: the DC PV system disconnect, could be the PV system electronic power converter, distribution equipment associated with the system. At least one of the following, doesn't have to be everywhere, and again, only has to be the highest maximum DC system voltage calculated in accordance with 690.7. Well, here's something exciting, a whole new section. We just jumped forward out of Article 690 into Article 705. And 705.11 is supply side connections. Whole new section, exciting stuff here. Now we know that 230.82 allows us to connect equipment to the supply side of the service disconnect. 230.82.6, PV wind energy storage systems, other interconnected power production systems are allowed. They have to have a disconnecting means that's listed as suitable for service equipment. That's not a huge burden by any stretch. And we have to follow overcurrent protection as dictated in Article 230 Services, Part 7. There's an example of a supply side connection, right? We have a connection between the meter on our primary power source and the main service disconnect in the service panel here. The output of our power production source is connected in between. So let's take a look at some of these new requirements. Some of them previously existed. There are some new requirements in here, and we'll also take a look at some other sections that have impacts on supply side connections. So 705.11a, hey, the rating of the output, the continuous output current, cannot exceed the service conductor ratings. That is not a change that previously existed, pretty sensical. The service conductors have to be big enough to handle what the supply side connected system can provide. Okay, now there is an exception here. We'll talk about power control systems in just a few minutes. The conductors from the point of interconnection to the first overcurrent protection device have to be sized in accordance with 705.28, very similar to the requirements for in Article 690 for the output of electronic power converters. And it has to be at least 6 AWG copper or 4 AWG aluminum. We follow the installation requirements in 230.30 and 230.43 for underground or service entrance conductors. Overcurrent protection for supply side connections is sized in a similar means as that laid out in Article 690 for the output of electronic power converters. Now, if we're using fuses, the disconnecting means has to be on the service side of those fuses so that when the disconnect is open, the fuses are isolated from the primary power source, typically the utility grid. Let's take a look at the location of the overcurrent protection devices. Connections outside the building have to be readily accessible. They can be inside, basically at the first location where the conductors enter the building. Once again, readily accessible. We have different requirements based on the type of building we're working on. Inside the building, we can have up to 10 feet of conductor length from the point of connection in a dwelling unit. If we're in a non-dwelling unit, we can go up to 16.5 feet of length. If we are in a non-dwelling unit, and we have cable limiters within 16.5 feet of the point of connection, then we can have up to 71 feet of total conductor length before we have our overcurrent protection device. So different ways to limit the amount of conductor exposed to the output of the utility grid or the primary power source before we get to the overcurrent protection device. Now, how do we actually make those connections to the service conductors laid out in 705.11d? We've got to use listed connectors, follow 110.14. Got to make sure we comply with enclosure fill requirements, adding a bunch of additional conductors and terminations inside an enclosure, make sure there's room for it. If we're making any modifications, we want to follow manufacturer instructions. You may have to get it evaluated in the field and field labeled. That could be an option. If you want to make a connection in a meter socket or in other equipment that's under utility control, those connections have to be approved by the utility. Don't cut the little lock and open it up and go in there. Always consult with the utility first. Also take a look at 230.46, some big changes in 2020 for splicing and tapping service entrance conductors. Devices must be listed. Power distribution blocks must be marked suitable for use on the line side or equivalent language. And as of January 1st, 2023, splice devices and pressure connectors must also be marked in a similar means. So there's some examples of various connecting methods for supply side connections on the screen here, and we'll see that those are going to need to be listed and marked based on some of these 2020 changes. We have to turn to 250.25 for new 2020 requirements on grounding systems connected on the supply side. And these apply when the disconnect and overcurrent protection for that supply side system are in an enclosure separate from the service equipment. So we're going to break it up into two categories, a grounded utility supply system and an ungrounded system. We have to comply with 250.24A through D when we're looking at a grounded utility system. We have to bring a grounded conductor to each service disconnecting means, and that's going to apply to the supply side connected disconnecting means. And we have to connect the grounding electrode conductor to the grounding electrode, the EGC, and the enclosure. We have to bond that together with the grounding electrode conductor. If we are connecting to an ungrounded utility supply system, we comply with 250.24E, and the grounding electrode conductor is going to connect to the grounding electrode and the metal enclosure of the service conductors between the load end of the meter and the service disconnect. So how we make those connections varies based on the utility supply system, but we're basically treating this essentially as another service disconnect. We're not necessarily calling it that, but in terms of how we're grounding it, it's going to very much look that way. So here's an example of a connection to a grounded primary power source. We've got our neutral conductor coming into our AC main service panel. A grounded conductor is brought to the service disconnecting means, calling that the PV system disconnect here. You can see in that disconnect, it is on the service side of the fuses that are located in there. And there's a bonding jumper connecting the grounded conductor to ground. And we have the grounding electrode conductor connecting that grounded conductor, the equipment grounding system, and the enclosure itself back to the grounding electrode system that's already connected to the service. Now, you do want to consult the EPC manufacturer. You may or may not be required to run a neutral conductor to the electronic power converter itself. That's going to depend on the particular inverter or other EPC that you are using. We're not going to look at all of 705.12b because there are it's mostly the same. 705.12b36, a new option, however, in 2020, and this is with regards to panel boards supplying feed-through conductors. So connections to bus bars of panel boards supplying feed-through conductors. And there's an example shown on the slide. We've got our primary power source breaker on the top. There's some room for some branch circuit breakers. And then at the bottom, we've got the feed-through lugs, which could supply another panel. You know, basically, that feed-through is an extension of the bus bar. And it's going to carry the bus bar, that is going to carry the load of the breakers connected to it, plus the load on the conductors connected to the feed-through lugs. Pretty obvious, right? The grid's going to supply the branch circuits and the feed-through lugs. Now, those feed-through conductors are also going to be able to carry whatever is available from all power sources, right? So it's going to carry whatever the load is, but that load is going to be able to draw on both the primary power source and, if we have any other power sources, that as well. So it's really not that different than the rules we've used in the past when we think about sizing bus bars that have multiple sources of power connected to it. That feed through is really just an extension of the bus bar, and we're going to treat it pretty much the same way that we have for feeders and bus bars in the past. Okay, let's take a look at the two choices that we really have. We can go bigger, or we can reestablish overcurrent protection. So we're really just looking at the feed-through conductors at this point. We also have to consider the bus bar in that panel itself, where those rules are well established in a place already. So 705.12b36. First option, size the feed-through conductors as feeders, which is laid out in 705.12b1. Right? So we have to consider the two sources of supply current, the primary source, the grid typically, and whatever the electronic power converter or PV system can supply. That's going to be its maximum output current times 125%, how we calculate maximum current. So whatever the rated current from the manufacturer is times 1.25. So here's an example. We've got our primary power source coming in. We've got the main overcurrent protection device, branch circuits, the feed through coming out to another panel from the bottom. If we connect another power source, well, now we can supply more power. Hey, if we make those wires bigger, it can handle both sources of power. So that's one option. That's one option. Now, we're not talking about the bus bar. We're not talking about the bus bar. The bus bar inside of here is still going to be subject to the same rules in 705.12 that we've used and applied for years. Multiple power sources connected to it, 100% rule, 120% rule, whatever those options that we may want to use. The other method that we could use when we have a panel board supplying feed-through conductors in regard to protecting those feed-through conductors would be having overcurrent protection on the supply end of the feed-through conductor. So this would be what we would call a sub-feed breaker. Essentially, we are reestablishing overcurrent protection on those feed-through conductors at the level that was previously supplied by the main overcurrent protection device before we added the power source output circuit. So if this was a 200 amp main overcurrent protection device and we had sized our sub-feed conductors through, or our feed-through conductors for that 200 amps, well, putting a 200 amp sub-feed breaker on there reestablishes that, reprotects the conductor, even though we've added a second source of current to that bus bar. As I've mentioned, that bus bar, we still got to consider the multiple sources of current that are being supplied to it. So we turn back to 705.12b3, 1 through 3, right? The 100% rule, the 120% rule, or the inverter combiner panel. We don't have time to go into those. They didn't really change in 2020 anyway. Another big addition to the 2020 NEC is an answer, at least one answer, to the question of how do you add energy storage to a service that's already maxed out with PV, right? We've got an example here on the slide. We've got a 200 amp bus bar, 200 amp main overcurrent protection device supplied by the utility grid. We've got a power source output circuit connected in the bottom of that panel that is rated at 32 amps. We probably got a 40 amp breaker in there being backfed. We are maxing out this panel under the 120% rule in 705.12b. So what if we want to add energy storage? What do? We can't put any more current onto this bus bar. We can't add any more power sources. Yeah, sure, we could rip it out and put in a bigger supply, 400 amp panel, increase the service. That's expensive. We don't really want to have to do that. We can, but maybe there's another option, and that option would be something we're calling a power control system. Okay, so new addition to the 2020 code, power control systems. And as the most simplistic look at it, we take a PV system, for instance. We take an energy storage system. We connect them to the power control system, and the power control system limits current to the bus bar or conductors that it is connected to. It's going to take what's available from these two sources and make sure that whatever comes out of it never exceeds what the bus bar that it's connected to can handle. Together, those two sources could exceed what the bus bar can handle. The power control system prevents that from happening. Now, we're not showing, this is a pretty simple diagram, we're not showing current transformers, monitoring, communication equipment that is going to be required to make this happen, the brains behind it, the monitoring behind it, the control of it. But this is a pretty simple idea on its most basic level. So 705.13, power control systems, new in 2020, controls the output current of one or more power sources, energy storage systems, or other equipment, maybe an electric vehicle power transfer system. There's lots of options that we can bring together. PV systems, batteries, fuel cells, generators, electric vehicle power transfer systems, all coming together on one bus bar through one power control system. That gives us the capability of ensuring that that service equipment or that bus bar is not overloaded by limiting the current to protect the conductors and bus bars supplied by the PCS. Now, the listing of that PCS may say, hey, it's an overcurrent protection device as well, or overcurrent protection may be required independently. It depends on the gear. So that really gets into the listing of a power control system, right? So the PCS are listed and evaluated to a UL CRD, Certification Requirements Decision. The CRD was developed and added to UL 1741 SA to allow compliance with this new section of the NEC 70513, Power Control Systems. So power control systems and inverters may be tested and qualified for non-export and or limited export to the grid or power or primary power source. Right? So they can disconnect completely, they can limit the amount of export, that way limiting the amount of current on the bus bar or conductors that they're connected to. Now, realistically, right now, it says 720 on the slide. Even as of now, there's not a whole lot of options out there for this. There's a couple, and there's a lot in the works, and we're going to see more and more of these coming as energy storage becomes a bigger and bigger part of what we do. So you really look for this happening. This is a good example, though, of the code being there and setting the stage to allow for this to happen as we get more and more options. Now, when it comes to power control system 70513A monitoring, it must monitor all currents within the PCS, the controller. Otherwise, how is it going to limit it? How is it going to know what's happening? Right on the load side, so on the load side of the service disconnect, any bus bar or conductor not monitored by the PCS has to comply with the rules in 70512 for load side connections. Of course, nothing surprising there. It's not monitor controlled, so we got to make sure it's protected by these other existing rules. So the example would be the 120% rule applies to the bus bar a PCS is connected to unless the primary power source current to the bus bar is monitored. So if we have CTs on the input from the grid to the bus bar so that we can monitor it and react so that we don't overload the bus bar with the other power sources that the PCS is controlling, well, yeah, then we have to follow that 120% rule. Now, PCS is on the supply side, which we can certainly do as well. They have to monitor and prevent overload of the service conductors. This is very much in keeping with the idea in 705.11a. The service conductors are sized to handle what they can handle. Let's limit what we put on them to whatever that number is. Nothing too out of the ordinary there. 705.13b and e, settings and access for our power control systems. All PCS controlled currents plus all monitored currents from other sources have to be less than the ampacity of the bus bar supplied by the power production sources. Okay, so I think that's pretty straightforward. It's a lot of words to say, hey, we got to control what's coming in, monitor what else is coming in, and together they can't exceed the ampacity of the bus bar or conductor. Now, if the PCS is connected to an overcurrent protection device that protects that bus bar and it's not monitored by the PCS, we've got to set the controller, the PCS controller, below the rating of that overcurrent protection device. We don't want to allow more to go onto that OCPD and potentially trip that OCPD. More go onto the bus bar and trip that OCPD. Right? We don't want nuisance tripling because the power control system is putting out more than the OCPD protecting the bus bar that it's connected to. If it's monitored and we have the capability to react and not go above that current level, then we don't necessarily have to comply. For 705.12a through e, we're going, when we look at load side calculations, the power source output circuit current, the value we're going to use when we do these calculations, is going to be based on the setting of the PCS controller. So it may have a range of output currents. You're going to set it at a certain value based on the particular application and the particular equipment you're going to connect it to. That value, not the maximum value of the PCS, becomes what we use for circuit current sizing when we start looking at 705.12a through e, for instance. Now, E, 705.13e, does say, hey, okay, let's slow down for a second here. If we are going to be basing the protection scheme on settings, those settings have to be behind covers. They got to be locked or password protected so that they're restricted to qualified personnel only, right? You can see 240.6, these requirements are clearly laid out there. We don't want somebody to just be able to crank it up and all of a sudden we don't have the protection of the PCS anymore because the setting's been cranked up higher. 705.13 C&D, OCPD, and single power source rating in regards to power control systems. The PCS must provide overcurrent protection. It could be in the circuits of the PCS, or the PCS could be listed with overcurrent protection device functionality, either because it has included breakers or OCPDs in it, or through other electronic means. In regards to the single power source rating, the rating and ampacity of the bus bars connected to the PCS have to be greater than the rating of any single power source OCPD controlled by the PCS. And that, again, it's a lot of words. It says something pretty simple. If I've got whatever the biggest breaker is that the PCS is controlling, I've got to make sure my bus bar can at least handle that output, at least handle whatever that largest connected power source is. Now, if we have more than one, whatever the biggest, we want a size for that, and thus we'll be able to handle all of the other ones. This is just kind of an example of what a PCS could look like. Starting on the left-hand side, we've got a PV system connected into an AC combiner panel. There's an energy storage system with a battery management system and inverter also connected in there. We've got monitoring, communication. The PCS has load breakers, has an input from a generator potentially, an input from a primary power source. It's able to disconnect and operate in island mode if need be. It may or may not have a neutral forming transformer in there. It's got a controller and brains, the special sauce of the particular PCS. Of course, this is just kind of a generic diagram. As we start to look at individual specific products, you're going to want to, of course, look at the manufacturer's diagrams and follow their instructions and manuals. Okay, let's jump into Article 706, Energy Storage Systems. At 706.1, the scope applies to systems with capacities greater than 1 kilowatt hour, 3.6 megajoules. This is new. So we have clear guidance when and where this does not apply, Article 706. And really what we're trying to do here is not make it apply to things like backup batteries and exit lighting, for instance. Small batteries. We're really looking at larger energy storage systems greater than 1 kilowatt hour in capacity. It can be standalone or interactive. These primarily store and provide energy during normal operations. Okay, so they're not necessarily there just as backup power. They are interacting with the grid. They may be peak load shaving. They may be performing other functions, but that is, their main goal: store and provide energy during normal operations. Now, this one is okay. Informational note number 2, there can be a subtle distinction between a battery storing energy and an energy storage system. A battery storing energy is not necessarily an energy storage system. See Article 480. An energy storage system may be comprised of battery storing energy. See Article 706. Clear as mud, not really what I'm looking for here in terms of giving us good distinctions when we need to follow Article 706 and when we need to turn to Article 480 for storage batteries. Now, there are a few things that are going to kind of dictate this, and we'll look at that here now. The listing requirement. New in 2020, energy storage systems must be listed to UL 9540. Required. Now, this may be a system comprising a UL 1973 certified stationary battery pack and a UL 1741 certified inverter. They may just be all together one system listed to UL 9540. This is a change in 2020. Other building codes require UL 9540 for residential applications, the IRC, NFPA 855. It goes to show you got to know all the codes. Now, this is also something that, the codes need to homogenize and make their language consistent. And we're seeing this happen here now in terms of this listing requirement in 706.5. We'll talk about 480 and that in just a minute here. 706.15, disconnecting means required for all ungrounded conductors derived from an energy storage system. It could be built into the energy storage system. It may be an external disconnecting means. Now, new in 2020 is a requirement for 1 and 2 family dwellings that we have the disconnect or a remote actuator at a readily accessible location outside the building. So new requirement for 2020, outside the building. Now, there's also a new requirement for emergency service shutdowns for 1 and 2 family dwellings outside the building as well in 2020. We may or may not touch on that. But this is kind of a big one here. It's got to be either the disconnect or a way to disconnect that system with a remote control or actuator, readily accessible outside the building. So not readily accessible inside, not non-readily accessible outside, readily accessible outside the building. That disconnect has to be marked as an energy storage system disconnect. It's going to have the nominal AC and maximum DC system voltage. We're not going to go into the additional marking requirements for non-1 and 2 family dwellings. If applicable, because we have multiple sources of power here, we may have DC sources on one side of the system disconnect and the battery on the other. We may have an AC on one side and the energy storage system on the other. If the terminals in that energy storage system disconnect can be energized when it's open, well, you got to mark it as such. Terminals on the line and load side may be energized in the open position. Okay, 480.3. Now, this is where things get a little muddy. We talked about the capacity requirement below which Article 706 does not apply. We talked about the fact that in order to be an energy storage system, it's got to be listed to UL 9540. 480.3 says, hey, storage batteries and battery management equipment must be listed. This applies to lithium ion and other battery chemistries, but it does not apply to lead acid batteries. Lead acid batteries do not have to be listed. In some cases they are and maybe and can, but they don't have to be. Now, as I said, 706 as well as other building codes require UL 9540 listing for residential applications, which kind of puts us in a little bit of a bind here, right? Puts us in a little bit of a bind because now it may be that it's tough to install stationary storage batteries that are not listed in 9540 in residential applications. Going to want to work with your building departments and AHJs to figure out their interpretation and what's going to be allowed and what's not. Again, only for residential applications, but this can be a big deal because we've been putting lead acid batteries in place in these kinds of systems for years and years and years, but codes and standards are changing, and that's going to create a little bit of a gray area and murkiness for a while here. As I mentioned, 9540 may include, 1741 inverter and an appropriately listed battery pack as well to meet those requirements, or it may be an all-in-one system. Lead acid batteries, not required to be listed. Disconnects for 480.7 required for systems with a voltage over 60 volts DC. Look to F for the labeling requirements. Much like with energy storage systems and services, there is now a requirement for 1 and 2 family dwellings for an emergency disconnect. So new in 2020, again, that disconnect or remote control means have to be located outside the building in a readily accessible location, and they have to be labeled as an emergency disconnect with a nominal battery voltage. So different ways to accomplish that. This is going to add, in many cases, some cost and extra equipment to these systems, but the idea here is that the ability to disconnect these power sources and disconnect them from what other circuits they may be supplying is of value to first responders and other emergency personnel. Lastly, Article 710, standalone systems, new in 2020, relocated from 690. Okay, in 2017, 690.10 was standalone systems. That's gone. It's all been moved into Article 710, its own article, because guess what? You don't have to have PV to have a standalone system. You could have a generator and energy storage, or a generator and batteries, or you could have a wind system or a hydro system or whatever. You maybe have PV too. There's no reason for those rules to live in Article 690, which is about PV systems. Okay, so it applies to power production sources operating in standalone mode. Could be a pure standalone system, OG, off-grid, old school, no primary power source. You make it, you store it, you consume it. Can also apply to multi-mode equipment that's never connected to a primary power source. So it may be an inverter that's listed to interconnect to utility grid, but it hasn't been connected. Now, there's lots of different system configurations here. PV is not required. Energy storage is not required. But the rules that you'll see in Article 710, very familiar. I don't think there's any changes, very minimal. Mainly what happened is a relocation from Article 690. All right, well, that was a quick look at the changes in the 2020 NEC. Hope you enjoyed it. If you have other training requirements that you're looking to meet, whether it's for yourself as an individual, for your company, for your organization, please visit us online. There's a code on the screen here for $50 off our September courses. That is also good for October and November courses as well. Forgot to update the slide. My apologies there. We do have safety training online that is highly recommended, very discounted pricing, focusing on residential and commercial rooftop applications, and a separate class on large-scale ground-mounted PV installation safety specific to PV. It's really easy to get a lot of safety training out there. It's hard to find stuff that's specific to what we do in the PV industry. So I'd encourage you to take a look at that. And if you need other continuing education, we have lots of options available online, including an 8-hour version it goes into much more depth on the 2020 NEC, as well as numerous other continuing education classes. Well, I want to thank you for joining us. Thanks from Solar Energy International, and I hope you enjoyed it, and I hope to talk to you again sometime soon. Thanks.
Hello, and welcome to this training on residential energy storage. My name is Kelly Larson. I've been working in solar since 1996 and teaching for Solar Energy International since 1999. I started my career working for Alternative Energy Engineering, which is now called AEE Solar. I designed and installed off-grid systems in California for about 20 years. Now I am contract design and field services, mostly for SEI Professional Services, which is the for-profit branch of Solar Energy International. We at Solar Energy International realize that everyone is affected by the COVID-19 pandemic, and we've stepped up to offer more online training and some discounts for you. We are offering SPI attendees a special deal, a discount worth 50% off our online courses. As you can see here, we have several courses that range from introductory PV 101 all the way up to our operations and maintenance course for more experienced technicians. We cover batteries and also have a technical sales class, so 50% off each of these courses. We also offer a battery safety class that is free to those in the U.S. and working in the solar industry or prospective solar energy workers. Find more details on our website and solarenergy.org or give us a call. We also offer continuing education courses on demand. You don't have to wait for a new session to start. These cover different short topics like the changes to the 2020 National Electric Code that are relevant to the solar industry, basics of site analysis and tips, tools, and techniques of the solar energy, for instance. And we are adding more new continuing education classes regularly. So if you're going for your NABCEP or need continuing education for recertification, the SEI classes are excellent, and it's your opportunity to join the more than 75,000 SEI alumni. Before we begin, I'd like to share a couple of terms that you might see. First of all, if you see grid, utility, or power company, or grid utility even, those all mean the same thing. Also, loads are anything that uses electricity. Off-grid and standalone systems are the same, and grid-tied or grid-direct are also the same. We also name one of our loads panels isolated loads, but you also might see that as backed up loads or something called essential loads. The most common PV system configuration is the grid direct system. This system eliminates the batteries, charge controller, and associated maintenance and cost, but it requires the grid to be present to function. Energy flows from the PV array into the inverter, which changes the DC electricity to AC electricity. This AC electricity then flows into an AC service panel, sometimes called an AC load center or a breaker panel, to operate any active loads in the house. Any extra energy is pushed out onto the utility grid. Notice that the arrows in these diagrams, they have a dashed line on the DC side and a wavy line on the AC side. Notice this around the inverter. On the PV array side, it's DC, so you have those dash lines there. And on the AC side of the inverter, it's AC, of course, and so that you have those squiggly lines. This inverter, the grid direct inverter, is a one-trick pony, and then it only converts the DC of the PV array to AC to be used for AC loads or to be fed back to the grid. It also has a special feature that it shuts off immediately if the grid is unstable or not present. When the amount of energy being produced by the PV system is less than the total AC load, then electricity from the grid makes up the difference. When a PV system is not producing anything, like for instance at night, then the house acts as if there was no PV system at all, with all the electricity coming from the utility grid. When the grid goes down, like as in a utility failure, brownout, or blackout, the grid direct inverter is designed to shut off instantly in order to ensure that no electricity is sent out onto the utility lines where it can endanger utility workers to working to restore power. Since the grid direct inverter is about 95% or more efficient, the PV power efficiently runs AC loads during the day. Grid direct systems are very effective at certain situations, but in many cases, energy is needed when the sun isn't shining. Batteries store PV energy so that it can be used during other times of the day. Batteries store DC energy, the same type produced by the PV modules. Batteries are the most expensive part of a system, so we want to make sure they are charged. That way they will give a long lifetime. We use a charge controller or an inverter charger or a battery management system. And the main purpose of all of these chargers is to regulate charging. A charge controller is a kind of like a smart switch. It allows PV to charge batteries until the batteries are fully charged, and then it cuts off PV to protect the battery. Let me share a word about battery chemistries. Lead acid has been the standard for about 100 years and still is a good budget choice. There's flooded, used for hard charging and discharging, and sealed, AGM or gel, used for situations where no maintenance is possible or in very cold locations. The lithium technology is commonly seen in PV systems and for battery backup is called lithium iron phosphate, or LFP, or nickel manganese cobalt, or NMC. With lithium chemistries, there's a chance of explosion and fire, as we have seen with the hoverboard incidents. The benefit of lithium ferrous phosphate or lithium iron phosphate, this lithium chemistry is the least likely to explode or catch fire. With lithium cells, we usually call that charge controller a battery management system, and sometimes you'll see it abbreviated as BMS. As contrasted to grid direct systems that have utility interactive inverters, we have an inverter charger when batteries are in the system. These inverters can operate without the grid and connect to batteries as their DC source. The inverter charger can operate without a grid connection, and it can also charge batteries from an AC source. The multi-mode inverter is a special inverter charger that also has the utility interactive feature built in to connect and feed back to the grid. Now keep in mind that inverters are not 100% efficient. Every time we change energy from one form to another, we have losses. A grid direct inverter is highly efficient, about 95% or more, but battery-based inverters are not nearly as efficient. Here's a very simple diagram of a standalone PV system. This is called standalone because it isn't connected to the utility grid. This inverter also has an AC charger useful for charging batteries from an AC energy source, like a generator or utility. Here's a very simple diagram of a standalone PV system. The system is called standalone because it isn't connected to the utility grid. This has an AC charger that's useful for charging batteries from an AC energy source, like a generator or the utility grid. So even though this inverter isn't utility interactive, it can still charge batteries from the grid. Now, many battery-based inverters can function as backup power systems without a PV array. In that case, the batteries are strictly charged by the grid, a generator, or both. A PV generator hybrid system uses PV as the primary charging source for the battery bank, with a generator that can be turned on manually or automatically to keep the batteries charged when it's cloudy or when the batteries need extra charging. Let's look a little more at standalone PV systems. Batteries allow stored energy made from the sun to be used anytime at night or cloudy days, for instance. And contrasted to PV direct systems, where there's just a PV array and a special DC load, with standalone systems, you're not needing to buy a special load, but can just use standard AC loads. Plus, the batteries provide a buffer between the varying PV array output and those loads. You can run both DC loads directly off the batteries or AC loads off of the inverter. In fact, with this system, you can wire a building with standard loads and run it, although you'd want to get as efficient loads as possible. Most quality inverters have a built-in load control that protects the batteries from over-discharge. But remember to check those settings, as lead-acid batteries may not be sufficiently protected. Here are some of the applications of standalone systems. Just think about all the places where a standalone system may work well. Examples are places where there is no grid, it's expensive to connect to the grid, or systems cannot feed back to the grid. Also where the grid is unreliable, where there are public safety power shutoffs, for instance, and areas where there are storms or other natural emergencies. With or without solar, these systems can provide power without the grid. Now remember, unless it's a multi-mode inverter, it can't feed back to the grid and get credit from the utility. Now expanding the system a bit more and showing a couple of new terms, here is a DC-coupled multi-mode system, also known as a grid tied with battery backup. You'll notice that we have an isolated loads panel in this system. That allows us to isolate the loads we want to back up. This is because most customers can't afford to back up their whole house for long enough to be useful. But the DC-coupled multi-mode system also has a multi-mode inverter which can operate in two modes. It can tie to the utility grid just like a grid direct system, but when the grid is down, it provides backup power for certain loads like the standalone system does. Note that in the grid outage, the multi-mode inverter cuts off connection to the utility grid, and the loads in the main AC service panel will not be powered. When the grid is operational, the multi-mode inverter can take AC from the grid and charge the batteries or power loads. A generator can also be connected to the system for longer standalone operation. Note that there are different ways to program and design multi-mode systems. They can be configured to regularly charge and discharge the batteries to maximize what's called self-consumption and to minimize grid power consumption. They can be programmed to never allow solar energy to flow back to the utility grid in a zero-cell type of grid-tied system. Now, the heading of this slide contains the term DC coupling. Notice the power the PV array produces goes to the battery without being converted to AC. That's why it's called a DC coupled system. So what are the pros and cons for DC coupling? Well, since the batteries are charged with the PV, which is DC, there may be higher system efficiency due to no AC to DC conversion to charge the batteries. This is especially true for systems that store energy during the day and power loads at night. We'll see the alternative way to do this called AC coupling in a minute, which uses an inverter between the batteries and the PV array. But in DC coupling, the charge controllers tend to be a less expensive option than grid direct inverters in AC coupling. Note that there can be a glitch in the AC coupling, which doesn't happen in DC coupling since the batteries can be charged even when the inverter goes into low voltage disconnect. Every time energy is converted from one form of energy to another, like AC to DC or DC to AC, there is loss. So DC coupled systems are more efficient for systems with DC loads. The system only needs one inverter, which doesn't require communication with the charge controller. Also, a larger array is possible relative to the inverter size since the battery is charged prior to the inverter. Some disadvantage of DC coupling systems are that the PV array voltage may be limited. Many charge controllers are designed for 150 to 300 volts PV arrays, and a few go up to 600 volt PV arrays. Grid direct systems have 600 or 1,000 volt PV arrays, so that increased voltage can save us in wire costs and equipment also. DC coupling is more complicated to retrofit into existing PV system that's grid tied. It requires much rewiring and some different equipment. The DC coupling system may only be able to charge battery from solar, not the grid, depending on if it has an AC source and an AC battery charger. I mentioned AC coupled systems, so let's talk about those now. Here is an AC coupled multi-mode system, also known as a grid tied with battery backup with AC coupled. Up here in the upper left-hand corner, you can see the PV array and a grid direct inverter, which could have been part of an existing grid direct system. You can also do this with microinverters and individual modules connected to microinverters as opposed to a whole array and a grid direct inverter or several grid direct inverters. It's all equivalent. Just like in the DC coupled system, we put the backed up loads in the isolated loads panel. The isolated loads panel is then fed by the multi-mode inverter. The battery is charged from the AC charger in the multi-mode inverter. This energy can come from the array or from the grid. Notice that in AC coupled system, the power produced by the PV gets converted to AC prior to the batteries. This is less efficient for charging batteries, but more efficient for AC loads. That's because the grid direct inverter is highly efficient. Following the energy flow, PV produced energy flows through the grid direct inverter to the AC bus, as we call it. The AC output of the grid direct inverter first operates loads in the circuit in the backed up loads panel, and if there's a surplus, it flows into the multi-mode inverter charger. If the batteries need charging, the multi-mode inverter charger converts the AC electricity back to DC to charge the batteries. If the batteries are full, or if there's more power than needed for battery charging, then it flows back to the service panel, the AC service panel, and runs those loads. Now, if there's still any surplus after providing power to the loads connected to the service panel, assuming the system is net metered, the power can then be sold or exported to the utility grid. Just like the previous example, if the utility grid goes down, the multi-mode inverter automatically disconnects from the main service panel, isolating the system so that only the loads in the backed up or isolated AC loads panel would have power. Both the PV system and the batteries can provide power to the backed up loads in that panel. The AC coupled system really shines when it has to serve many locations, like in a village. The buildings can be wired up with standard AC, and a microgrid can be set up to link different sources like grid-tied PV systems on one building to battery banks in another, and loads dispersed in all the buildings, for instance. Regardless of whether the PV system is AC or DC coupled, net metered, or zero cell, the multi-mode inverter can also use power from the utility grid to charge the batteries if desired. And again, depending on local regulations, the system could be programmed to operate in peak load shaving or load shifting modes, using battery power to offset utility consumption at times when the price per kilowatt hour is higher. So, depending on whether the system is grid-tied or standalone with battery backup, spread over a large area, has multiple sources, the scale of the consumption, or battery retrofit to existing grid direct PV system, we might choose AC coupled versus DC coupled. So if the system has an inverter between the PV array and the batteries, it's called an AC coupled system. Now let's talk about a fairly new approach, the energy storage systems, which are usually lithium battery banks. with other stuff included usually. Now notice in the upper left-hand corner again, we have a PV array and a grid direct inverter, which is a grid direct system. It could be a standard existing grid direct system in the building that we're going to integrate into this new system that contains energy storage. Many customers want to add energy storage later to an existing grid direct system due to a situation of needing storage for certain loads if there's a grid outage, or there could be storms coming, or those kinds of issues. Any place where you have loads and you want them to have uninterrupted power to them, this can be a good solution. The market for energy storage products and solutions is growing, and new products are constantly being introduced. In fact, the 2017 National Electric Code introduced a brand new article, Article 706, for energy storage systems. As seen in the last few slides, multi-mode systems can be complex and involve many components. New ESS products are on the market in which many of the components are housed in a pre-wired manufacturer-provided enclosure, and the inputs and outputs like the PV array, AC service panel, batteries, isolated loads panel, etc., can be wired directly into the self-contained enclosure. This slide shows a PV array grid direct inverter system AC coupled through the isolated loads panel to a self-contained energy storage system. These self-contained energy storage systems commonly use lithium battery chemistries, and so there also would be a battery management system integrated with the batteries. If there is an existing energy management system, or otherwise known as sometimes load management system, in the building, some multi-mode all-in-one systems can be programmed to operate in coordination with them. Note that the equipment and functionality of the new types of self-contained systems vary widely with manufacturer, and if installing this type of system, it is imperative to refer to the manufacturer's recommendations to ensure that you have all the proper equipment and knowledge for a successful installation. UL Standard 9540 is for listed energy storage system products. Note, however, that an ESS may not be able to provide battery backup or connect to a PV array on its own. It might just be a battery, or the inverter may be a grid direct and not a multi-mode inverter. Always be sure to check with the equipment manufacturer to figure out the capabilities and use cases for a particular self-contained energy storage system. AC coupling has some advantages and disadvantages. For residential systems, a big advantage of AC coupling over the traditional battery-based DC-coupled PV system design is that battery backup can be added to an existing grid direct PV system without changing most of the existing system's wiring. An AC coupled system can be more efficient in powering loads than a DC coupled system when the batteryless grid direct inverter is doing the majority of the power conversion. The efficiency gain occurs when AC loads are being powered during high PV production times. This way, the AC power output from the grid direct inverter is used by the loads without ever reaching the battery-based part of the system, at which point additional conversion losses would occur. The typical efficiency of a battery-based inverter is generally in the 96 to 98% range compared to the 90 or less % range for a battery-based inverter. In an AC coupled system, the PV array is connected to a grid direct inverter, which means that the array can be wired at a higher voltage, like up to 600 volts for a residential system, or even 1,000 volts for a commercial building. This reduces the number of parallel strings required and therefore reduces the number of combiners and series fusing. Additionally, it can result in smaller conductors being required due to less current at higher voltage. Note that while this used to be a major advantage of AC coupled systems, some charge controllers are now rated up to 600 volts, so this advantage can be utilized in a DC coupled systems as well. AC coupling can be used on large scale for microgrids because when powering buildings that are far apart, a utility grid can be emulated using commonly available transmission equipment between sites in a microwave to reduce power losses. Also, it is easier to find skilled workers familiar with AC grid infrastructure. AC power microgrids can take advantage of AC coupled systems and simply adding grid direct systems to the loads panel located on each separate building or facility in the network. For AC coupling, charge regulation is a bit complicated. We'll talk more about this on the next slides. Low battery can result in difficulty restarting these systems. So for complex regulation, the devil is in the details. This issue is exacerbated by mixing different manufacturers' equipment that might not be able to talk to each other. Most AC coupled systems are for larger kilowatt size or starting from an existing grid direct system. We will need an experienced person to do the design and install on these systems. And there may be utility requirements and restrictions that will affect our decision between AC and DC coupling. In the next few slides, we'd like to walk you through the function of an AC coupled system and the charge controller issues that we've mentioned several times. This slide shows an AC coupled multi-mode PV system where the grid direct inverter is producing less power than required by the isolated loads and battery charging. This could be because of the amount of radiance is low, like due to clouds or the time of day, or because the total amount of load is high relative to the size of the array. All power from the PV system is output by the grid direct inverter as consumed within the isolated loads panel, and then the additional power needed by the isolated loads is provided by the utility grid, routed through the multi-mode inverter. In this example, the utility grid is also providing power to the battery bank to keep it at a full state of charge and ready to provide power in the case of a utility outage. Unless the batteries have been recently discharged, they will be in the float state of charge for lead acid batteries, or called the constant state of charge for lithium ion batteries. They're essentially being trickle charged and consuming very little energy. This slide shows an AC coupled multi-mode PV system where the grid direct inverter is producing more power than is required by the isolated loads and those in the main AC service panel, plus the power to battery charge. Notice the arrows showing the flow of electricity from the isolated loads panel, and they're going to the multi-mode inverter and then to the main AC panel and the utility grid. Enough power is produced by the PV system to provide for all of the loads within the isolated loads panel and the main AC service panel. Since the PV system is providing more than the loads need, the additional power is fed. This is typical of a net metering system, which is one of the most common interconnection methods for multi-mode systems. The programming of the system must be set correctly to ensure that excess PV power will be fed back to the utility grid. Again, assuming the batteries have not recently been discharged, they will be in the float or constant voltage stage, consuming just a trickle of current to maintain their program voltage. In this case, the current comes from the power output by the grid direct inverter, slightly reducing the amount of power available for export to the utility grid. Now consider an AC coupled multi-mode PV system designed to provide backup power when there is a utility grid outage. We call this island mode. In this example, the grid direct inverter is producing less power than is required by the isolated loads. Notice that now there is no connection to the utility grid and the system is isolated from the main AC service panel. Only the isolated loads are being powered. Since the PV array is producing less than the load's demand, power must also be drawn from the battery bank, inverted from DC to AC by the multi-mode inverter, and used to power the isolated loads. During a grid outage, the system is operating in the same manner as standalone system, but is only providing power to the loads in the isolated AC loads panel. Unlike many standalone systems, there is no other power source, such as a generator, present. Eventually, the batteries will discharge so much that the system may shut down if the PV power output does not increase or the demand of the loads does not decrease. A typical application for the system shown on this slide would be a site with unreliable utility and occasional short-term outages. This example shows the same system, again with a utility grid outage, which, as I mentioned, is called island mode. The grid direct inverter is producing more power than is required by the loads, and the battery is at a full state of charge. Since load and battery charging are not using all the power produced by the AC coupled PV system, the power must be regulated to avoid overcharging the batteries, which could possibly damage equipment and create a hazardous situation. The question here is, where will the extra power go? Or can we scale back the PV power being produced so that we don't have too much? This situation is a dynamic issue and changes often, so we need a reliable way to regulate while not wasting too much PV production. There are a variety of strategies to regulate power in which vary greatly by system type, application, effectiveness, and equipment manufacturer recommendations. The next slides will define the common methods of regulation for managing the output of the grid direct inverter in an AC coupled PV system. Battery voltage increases as they are charged. As the battery voltage gets up to a specified voltage set point that indicates that they are charged, the charging will need to stop. A multi-mode inverter can respond in several ways depending on how it's designed. Some modern multi-mode inverters change frequency slightly to communicate to the grid direct inverter to slow or stop producing power. This function is a way that the batteries can be protected from overcharge. Some grid direct inverters recognize this communication and can modulate its output to reduce power out to the appropriate level. If the grid direct inverter does not recognize frequency communication from the multi-mode inverter, then it will simply shut off when the frequency is higher than is acceptable for its range. Here's a chart showing the response of an inverter that can interpret the multi-mode's frequency change. So here the multi-mode inverter can change the frequency of the quote-unquote grid, the grid that the grid direct inverter is looking at. That's like the AC bus that I mentioned earlier. And so, for example, if the multi-mode inverter wanted the grid direct inverter to put out 50% of its rated power, then it could put out 61.5 hertz, and that would be the result. If the grid direct inverter can't recognize the changes in frequency, then we must use a relay to shut it off or use a diversion load to use that excess energy. In fact, the code requires that there be a diversion load in some systems as a backup to the normal regulation method. Lastly, we could use load controls, also called load management systems or LMS, to turn loads on and off to more effectively use whatever PV powered is produced. Load controls are being used more and more to optimize energy in use in buildings. And we focused in these slides in controlling the sources of power, but also controlling the loads open up myriad of possibilities for optimal energy use. This is an overview of the types of advanced functions that many multi-mode inverters and energy storage systems are capable of providing. For each different function, there are specific places and use cases where that function will be most financially viable and technically feasible due to the rate structures, requirements, and interconnection rules, site conditions, or customer preferences. The next few slides will focus on identifying the appropriate function and building a case for return on investment. So just to talk about these things briefly, peak load shaving is where some utilities charge a large fee based on the highest peak power, we're talking about watts, in the past. So wind tunnels or large factories, they use a lot of watts and just to turn on and to continue, but usually just the spool up is the biggest one. And so utility has to be ready to provide that power at a moment's notice, and that costs money. So they have traditionally charged demand charges for extremely large loads like the large wind tunnels, that sort of thing. Now those charges, though, are showing up in some areas on residential bills. Next, we have time of use, also called as TOU, load shaving. We ease power needs on the grid when the grid usage is up and the utility charges more. The next one is self-consumption. This is where you use what you make, and this option is popular in places like Hawaii, where net metering is restricted and kilowatt-hour costs are high. Zero export is when systems are not allowed to export energy, also something that has been happening in Hawaii, but I'm sure that we'll see it in other places as well. And grid support is used when the grid is unreliable and it's helped to stabilize the grid. And many of these advanced multi-mode functions came about to try and figure out how to help support the grid in this situation. So let's first talk about load shaving. As previously discussed, peak load shaving is an opportunity to reduce demand charges. So demand charges are based on the highest average power draw during a short period of time, often 15-minute intervals. And it's not based on energy consumption. So the demand charge is a multiplier based on the highest average kilowatt power draw. For example, if the per kilowatt multiplier is $8 and the highest average peak demand during a 15-minute interval recorded in a month is 34 kilowatts, then the demand charge on the monthly bill would be 34 times 8 equals $272. So these charges can make up a high percentage of a utility bill and are a very common component of commercial rate structures. Using stored energy from a battery to reduce peak demand daily and regularly can enable a customer to reduce demand charges. But solar alone cannot fulfill this purpose, as a single peak occurring during a cloudy day sets the demand charge for a whole month, or in some cases, even a year. If a peak demand does occur during a sunny time, then the solar can supplement battery power to pull down the peak. But solar alone cannot be relied upon due to weather variability or when the peak loads happen at night. Another common component of a rate structure is called time of use periods, or TOU. These are hours during which kilowatt hour prices increase, even doubling or tripling. The exact time period and duration of the peak rates is a variable from place to place and from season to season. Pulling energy from the batteries to offset loads during the peak period helps to lower the electric bill by consistently reducing the energy pulled from the grid during peak periods. Now, unlike demand charges, a single missed window won't affect the bill very much for a prolonged period of time. Some rate structures are tiered, such that every kilowatt hour above a certain bulk threshold costs more. If there is no TOU component associated with the tiered rates, batteries alone without a PV system cannot lower tiered pricing because it doesn't matter when electricity is used. But PV systems can very effectively lower tiered prices by reducing the energy purchased from the utility. This is a typical pre-COVID demand curve for residents. It shows when and how much power is being used average in a day. As you can see, as the family wakes up, demand increases before about 7 a.m. Home energy demand drops as they go back to school and work, and increases again as they return in the evening time. This utility is charging demand charges for the highest kilowatts, we're talking power, used in a 15-minute time frame per month. With metering, we can chart the appliances that are being used and how much energy they're using and when. And then we can calculate where the demand charges are coming from. Here is that residential demand curve again. We can identify an area of the demand curve that is causing the customer demand charges. We want to take the peak off the afternoon consumption from the utility. With a battery system, we could charge the battery at night when otherwise the consumption is low, and then discharge the battery to run our loads during this peak time to keep from having such high demand charges. Now, this requires sophisticated controls and careful programming. Load controls can also be implemented to reduce demand charges and in conjunction with a battery system can dramatically reduce or eliminate demand charges. Here are time of use charges imposed on a residential demand curve. The cost of electricity during the different time periods is noted here. We also see a clear sky PV production curve imposed on the chart in yellow. We see that in this case, during peak periods, electricity costs more. Note that rates can vary per season, so review the utility rates carefully. These charges encourage load shifting to off-peak times. Commercial and industrial facilities are the largest consumers of power and tend to operate during business hours, Monday through Friday. As a result, demand for electricity is highest during the typical work hours of the week, at least before COVID. On the other hand, most residences tend to have a reduced demand curve during the day, pre-COVID, when people are work or school and houses are empty. Some utilities manage this period of high demand by offering customers incentives to shift some of their power consumption, usually like larger loads like washers and dryers, pool pumps, and some types of commercial processes, to off-peak periods. This incentive is achieved by charging a customer a true cost of electricity per the economics of supply and demand. When demand for power is high during weekdays, the cost per kilowatt hour rises. During lower demand periods, say nights and weekends, the rate is lower. In the example above, during the summer, the on-peak price per kilowatt hour is more than 3 times the off-peak. These hours of time of use vary, and some utilities have multiple plans with different on-peak hours and with or without mid-peak hours. With peak load shaving, the goal is to curtail grid power demand and limit grid power when rates are high. We can program the inverter to use battery power instead of the grid to shave peak load. Here are some different methods of how this is done with battery systems. Some methods use current transformers, otherwise known as CTs, in the mains panel. The CTs monitor the load in the mains panel, and when the set point is hit, it supplies battery power. The peak shaving current is supplied from the battery inverter when the demand limit set point is read by the CTs. The equipment monitors when we need battery power and when we don't. Other methods don't monitor the loads, but have a timer function enabled for preset power output during non-peak time. For example, a time of use peak demand between 12 and 6, we could program the system timer to export a certain amount of power during that time frame to bring the peak use down. This is sometimes called a blind push. An example is, say, a 600 watts that's pushed for 6 hours in hopes that it'll shave the peak demand and keep it in a lower demand charge peer. In another method, the backed up loads panel is monitored via the inverter. Here, the peak shaving current is supplied only to the backed up loads panel, and all loads that we want shaved live in that backed up loads panel. This scheme doesn't push out to the main panel or do load shaving, only shaves in the backed up loads panel. Equipment may be programmable to operate backed up loads in standalone mode during on-peak hours with no power grid supplied, essentially disconnecting from the main panel. So back to the different advanced multi-mode functions, we talked about peak load shaving, demand charges, and time of use load shaving. Now let's go over the rest in our list. Self-consumption stores excess PV generation to consume later. Zero export, similar to self-consumption, but when the utility won't allow backfeed. And grid support is used when the grid is unstable, and it uses the battery and the PV power to help stabilize the grid. I mentioned that self-consumption and zero export are similar, but have subtly different programming and equipment needs. We can program the multi-mode inverter to use as much of the PV production on site as possible and can save money on our utility bill. Imagine a case where energy cost 20 cents per kilowatt hour to purchase, but solar power exported to the grid is only credited at 10 cents per kilowatt hour. The financial incentive is to reduce grid consumption while increasing the amount of solar energy that is consumed inside the building. The more solar power used to offset the grid electricity, the lower the electric bill will be, while solar power is worth only half as much exported for credit rather than being consumed on site. Now, this programming is sophisticated and requires a knowledge and experienced designer and installer. Zero export, also called zero cell, net zero, and grid zero, is similar to self-consumption, but in this case, the system is programmed to not allow power export from the PV or batteries to the utility. Note that we must confirm that the charge regulation method is suitable and prevents batteries from being overcharged. Here is a graph for a grid direct inverter's response to frequency. 62 hertz or above, and the inverter shuts off. More sophisticated controls allow for the inverter's output to be modulated instead of just on or off. HECO, the Hawaiian utility, was the first to widely introduce the concept of a zero export rate structure, in which absolutely no solar power or battery power is allowed to be exported to the grid from the building's PV system. Self-consumption, on the other hand, would be ideal for a rate structure in which export is not prohibited but is not financially beneficial. For a zero export system, monitoring the main service entrance with external current transformers, or CTs, is imperative, so the inverter can ramp down power exported to the main panel if the power pulled from the grid gets close to zero. For a self-consumption system, there may be looser configurations not based on CT-style monitoring. For example, programming the inverter to supplement consumption with stored energy during specific time periods, such as in the morning, with the idea that the loads are heavy in the morning, but PV power will recharge the battery later in the day when loads are lighter. That said, CTs could also be used to monitor circuits or specific loads to enable battery support when the loads are heavy, and battery charging when surplus PP power during the times when loads are lighter. Here is a zero cell or grid zero example of a DC coupled system. For example, a zero cell system is installed at a location with existing grid service and is designed to offset loads but not sell any excess power back to the grid. The objective is to prioritize meeting the building's consumption with PV-powered electricity while still having the grid supply available if needed to supplement PV production. Power is not exported to the utility. The utility is just used to supplement larger power requirements in the building or as a backup power supply. Here, power to all the loads is controlled by the inverter charger. The renewable source and the battery bank are prioritized first to power all loads, unlike the previous example of a multi-mode system where utility power, if present, is prioritized for the loads. If a smaller capacity inverter charger were used, the system would be wired like the previous multi-mode example with backup load type panel where the specific loads could be located. The wiring would be the same as the previous example, only the programming would be different. This could help strategically reduce peak loads and avoid peak demand charges, which in some cases can multiply the economic value of energy produced greatly. Zero cell systems are also being utilized in markets where high grid penetration policies and utility requirements are shifting. In some cases, this causes uncertainty regarding interconnection requirements and utility rates for consumption and generation. A zero cell system can remove some of the hurdles of connecting a PV system to a utility grid, particularly if there is no possibility of exporting power to the grid. It is possible to install a zero cell system without batteries using grid direct inverters that are capable of ramping back power if PV production exceeds the building loads. Specific equipment with monitoring controls must be installed for this, though. In some cases, the utility may require additional protective equipment depending on their analysis of the system. Be sure to understand the equipment manufacturer's requirements and recommendations. There are several challenges to integrating PV systems into grids. Some grids, such as Hawaii's, there are so much PV production that the grid would be unstable if they all shut down. The utility and these distributed energy resources, as they are called, or sometimes referred to as DERs, need to coordinate to keep such a grid stable. If a fault occurs on the grid, or if it is strained by high consumption, the DERs need to stay connected, and in some instances, change their settings to support the grid. This is behind the advanced inverter functions work being done. Stakeholders are working through how to handle anti-islanding, which refers to when a grid direct inverter immediately shuts down during a grid disturbance, characterizing what can happen if the inverter has a fault, developing advanced inverter function testing so that utilities know how the inverters are going to respond during a grid disturbance, and establishing secure and clear control communication between the utility and the DERs. A smart inverter working group was formed in 2013 by the California Public Utility Commission and the California Energy Commission. Manufacturers and utilities work together to specify autonomous functions that all inverters connected to the utility will be required to perform, including communications functions. This working group led to an IEEE 1547 standard that addresses what has become known as smart inverter functionalities. These updated functionalities are part of the IEEE 1547 2020 and are reflecting in the testing procedures of UL 1741 SA and SB. More and more states and utilities require that interactive inverters be listed to the new UL standards and be able to perform these smart inverter autonomous functions, including a set of mandatory responses to changes in grid frequency and voltage, as we mentioned before. Utility by utility, they are establishing the two-way communication protocols required to operate these advanced functions. These smart inverter functions allow PV to help the utilities stabilize the grid when it is strained. If the grid is unstable, the voltage or frequency goes out of the inverter's acceptable ranges. Without the smart inverter functionality, the inverter will just shut off. If the inverters were programmed to ride out the instability for a short time and stay online for maybe a few milliseconds during a grid disturbance, it could mean the difference between a more stable grid and a blackout. States including Hawaii and California mandate compliance, and all utility interactive inverters installed, including multimode, must document compliance with the jurisdictional requirements. Remember that every utility interactive inverter is required to shut down immediately if the grid goes out of its acceptable voltage or frequency range, unless the smart inverter functions are enabled. One example of a smart inverter function is to ride through for a brief time when the grid voltage or frequency is out of range. Smart inverters can now export or absorb volt amps of reactive power in response to a grid high or low voltage. They can also ramp inverter power up or down when the grid frequency goes out of a specific range. This makes the grid more stable. Note that compliance may require power ramping or operating at other than a unity power factor, which could mean lower compensation and provide no financial benefit to the customer or system owner. As these requirements become widespread, modeling tools incorporating smart inverter functionality requirements have to more accurately model system production. Currently, compensation for advanced inverter functionality for grid support is more likely to only be available on utility scale systems, but expect this to change. I'd like to thank you for joining me on this presentation of energy storage systems and invite you to check out our website, solarenergy.org, for more classes and information. I hope to see you soon, really, like at a show when they open up shows, or at our campus next year for a lab class or a in-person class. Otherwise, maybe I can see you online in one of our excellent classes. Thank you so much.